So welcome back. We're going to start our third lecture on our Destination Brazil initiative coming from Andifs. Today we're going to talk about comminution classification. So welcome to all of you who are here with us online, and for you who's watching us on YouTube, thank you very much for that. Okay. But before we start on comminution and classification itself, let us take a quick look on how things work out in the mining. So over the last two lectures, our last two encounters, we discussed a lot about mining in Brazil, especially what was critical and what kind of minerals are special to us, and we call this strategic minerals. And we talk a little bit also about the stage in a mine. I'm not going to talk about stages anymore, but now I'm considering and focusing only on active mining. Okay, so we're hauling the material, we're dealing with the material, and if we take a look at this situation, the first thing that we have to do during our work is taking a constant look on our resource and our reserves. Okay, we're going to talk a little bit more about this difference in a few slides, but just keep that in mind. There are two different things: resource and reserves. So we go to the field, we drill, we blast, and we got the ore. Okay, we have ore in our hands. What we have to do then is load and then transport this material. That is a silly mistake over there. It's not supposed to be drill over here. It's actually transport or sorry, haul the material. The best word would be like haul. It's just one L. It's supposed to be an exclamation mark, but it was terrible. And then we feed the mineral processing plant. Okay, so today we're going to take a quick look on those stages, and then we focus on mineral processing. So to summarize what I wanted to say before, it's all about the value chain. So when you take a look at the value chain on a mineral processing plant, it could be represented with something like this. Oh, just another one joining us. Okay. So the first thing is to take a look at the resources and the reserves. What we have and how much do we have? Okay. And we're going to go deep into that in a few slides again. Then we move forward to ore control. So I know where is the ore, what is the grade of the ore, and we're gonna come back to this technical words in a few minutes, but we have to know for sure what they means. That's of course, that's why we're going to come back to this. But as soon as we got a grip on where is the ore and what is the ore and the grades of the ore, we start the mining itself. That's why you have this block over there called mine, and it's covering 4 stages or 4 things that we need to do in order to produce: drill and blast, load and haul our material, and then we go to processing. So why I have this all separated over here? Because these two first, right here, it can be performed by geologists. I'm gonna put just the G letter over here. Okay, so our brothers, our best friends in this moment would be the geologists, and they're gonna cover these 2 stages. In Brazil, mining engineering can also do this. Okay, but typically it has been done by geologists. So mining engineer would be right here, right? Yeah, but in Brazil we also work in this stage. Okay, so again, in Brazil, mining engineering can do both. Actually, can do these 3 blocks over here. And when you talk about processing, it's not only about mining engineering. So chemistries plus mining engineering plus metallurgical engineering, we all work in here. And I know that in some countries, especially countries that study following the Spanish school, they would divide this. So if you're a mining engineer, you just do mine, that's all. So if you go to process, you would be automatically into the metallurgy. So you're gonna be a metallurgical, okay? So that's not the case in Brazil. So moving a little bit to the pen, to the left-hand side, after mining, what do I have? I have the processing and the market. So our lectures would gonna be focusing on this, but we can just let this gap open over here. So I'm gonna show you guys a little bit about drilling and blasting, loading and haul, because it's cool. It's really cool to see that big machines, that amazing machines working, and they are really big. And then we go to mineral processing. And I'm gonna do this because I want to fill this gap from drill and blasting, okay? And trust me, it is a gap from here up to here, okay? And we call this mine to mill. So I'm gonna show you guys a lot about mine to mill, and we're gonna talk a little bit later on a word, not a new word. It's been around for a few decades, I guess. But nowadays people are taking a really, really serious look at it, call it geometallurgy. Okay, so we're gonna talk a little bit about these two concepts. Mine to mill, it's more easy to implement, and I'm gonna explain everything for you, or at least a little bit about it for you. And we're gonna start with that. From that one, we can go to geometallurgy. So if you take a look then on the value chain on a mine, you could think in a chain, okay? Literally, you can think in a chain. So you have these links, and if you're working in one link, you're just gonna be on that link. You don't need to go to different links, okay? You don't need to know things like two links before or after yours. But that's not the case. That's definitely not the case. And we have to break this chain, because if you take a look, we're more like cogs, and we have to work together, okay, in perfect synchrony in order to have this machine work. So let's completely forget about this concept that mines are actually chain. Okay, we don't work like a chain, we work more like a cog. So we could take that first idea and translate into something like this. Oh, professor, you're taking ideas from circular economy. Something like that, okay? But one thing is for sure, I need to know where is my ore, what is this ore, the grades, the gangue minerals, the association with our minerals. So I need geology. I need a lot of geology in order to produce. After that, I need someone to taking care of all this data, and it is a big data. Okay, so if you can bring artificial intelligence with you into our problems, you'll be most welcome, because definitely we have a lot of data, and sometimes we don't know how to process this data. But after we define, okay, I'm gonna extract material on this part of my mine, okay, then I have to go there, and I have to drill, to blast, to load, to haul, and to deliver this to the mineral processing plant. And then we start to process the material. And after processing this material, of course, I just put an arrow indicating the market. That's not true. That's not the case, because unfortunately we produce things that we can't sell. Okay, so we have tailings being produced on the mineral processing plant. So I have to tackle with this also. But since we're going to focus on circular economy, I'm considering to produce everything, like zero tailings. I know that's not entirely true. That's quite impossible nowadays, unfortunately. It's like a utopia, but maybe in the future we could be doing something like that. Now, for now on, we're going to consider that the tail is going to be in the cycle. Okay, I'm gonna put the tails somewhere, and in the tailings somewhere, and in the future we're gonna come back to that. Okay, so starting with definitions, the first one is about mineral resource. So if you take a look at the chemical composition of mines itself, we're going to see a lot of elements, and some different elements like rare earth or even some PGMs, but it's going to be like ppm or ppb eventually, and you can work with that. So what for us is a mineral resource? It's a place in the earth that, or as you're going to see in the future, it's a place in the universe. Unfortunately, we're not mining the universe yet, but we will soon enough. So for now on, let's consider that is a place in our planet Earth that we have at a concentration of or an occurrence of a solid material with economic value. Okay. Oh, if it doesn't have economic value, it's not a mineral resource. No, it's just a deposit. Okay. So you have this anomalous grades, anomalous occurrence of minerals, but if you can't sell it, if you can't market it, it's pointless. It's just like a geological curiosity. Okay, you have this, it's okay, but you can't do anything with that. Okay, So if you can profit with that material, then you have resource. Okay, so this is resource. As you can see over here, we have a lot of geologists. Those are geology students, but on that stage, we need people off the ground. We need people wearing boots on the ground. That's the main word for us, or the main verb to us. It's go there, go to the ground and make evaluations. So if the reserve is actually economic, and more than that, if it's mineable, okay, if I can go there and extract that material, then I have resource. So this concept of mineable over here, we have to discuss a little bit more about it, because we have to understand that not every mineral I can actually separate from the game. And sometimes we're going to spend years trying to make some research over this, some technological development, and we just fail. Okay, and that's true. That's actually going to happen. So if you take a look at this, this is actually a mineral deposit. It's not a fake photo, and definitely we can see that we have over here something different that we have in here or in here. So this chunk of rock over here, this is different. And why I have this magnifying glass on top of it? Because this is a standard equipment for geologists, for field geologists, and they are over there taking a look and said, okay, this is important and this is not. Okay, and just consider this: my mineral, my economic mineral would be just these ones over here. Okay, so I have to separate those. I have just 3 parts of this material in all of that universe of particles. And how can I get only those? That's mineral concentration. Okay, and we don't have concentration for every single ore that we know. It's quite the opposite. We have concentration just for a few ores that we have in our earth crust. Okay, so that's why we have this definition: reserve. Okay, and reserve is something that we can have it. Okay, and we can sell it because we have the technology and we have the prices of this material. Okay? And the technology to produce this actually exceeds the price that we're gonna pay in order to do it. Okay, we're gonna profit. So if you're gonna profit, then you have reserve. But if you have only your mineral occurrence, you have just resource. And in order to take resource into reserve, then you have to work on that material and you have to spend money on it. And that's why I bring you this graphic. As you can see, you have 2 arrows, one to your right hand side and one to the bottom of the slide. And if you walk into these arrows, then you're increasing what? The level of knowledge that you have over this material or over the process in order to produce this material. So you're increasing your confidence. Okay, you're minimizing risks. And that's why it's so important to understand this, because you have to live with that all the time. Okay, so the results that we have after a geological exploration is going to always be mineral resource. Okay, so understand something: if you want to move from resource into reserve, you have to have more professionals working with you. You can't work only with geologists, because geologists, they're going to deliver to you resource. Okay, so then you need the mining engineer and eventually the metallurgical engineering in order to take the resource and come back with the reserves. Okay, and they're going to come to you and say, okay, you have 12 minerals buried in niobium in Catalan. We can only recover. What's recover? We can only produce. Let's consider that recovery as production for a moment. It's not, but we're going to come back to this term later on. But you can only produce 4 up to 6 of those minerals. The rest of it, you're going to lose it. Okay, you're going to have to put this on the tailing dams. Are you okay with that? Are you fine with that? And then we run our economic math, and we're going to come back and say, okay, it's profitable. We can do it. And then we start the mine. Okay, so if you fail in one of those links, and now I'm going to use the term link, you don't have a mine. But let's consider something. Everything that I told you before today, it's time related. Okay, so economic is time related. The demand for the material is time related. And the technology, in order to produce this material also depends on time. Okay, maybe it's not economic today, but it could become like 10 years or even more, a decade, 2, 3, 4 decades in the future. Yeah, that can happen. Okay, and it's actually happening right now. If you consider Europe, for example, they have many mineral resources that they used to mine in the past, and they decided it's not the time. Okay, because we have other reserves around the world that we could be exploiting right now and keep that reserves where they are for many reasons. One could be environmental reasons, but definitely it's also because of economic. It just doesn't pay off. Okay, so it's cheap to mine this somewhere else, and in the future we can come back to Europe as a mining continent. Okay, this is happening in the United States, Canada, even in Brazil. For some materials, we're having the same situation. If you consider iron ore in Brazil, as long as we have Carajás, we're not gonna be having a lot of iron ore mines in Brazil. Okay, but as soon as we run off Carajás, then other mines is gonna pop up all around the country, or at least in four states in our country. Okay, so this happens everywhere. And I think this graphic, this figure, it's not a graphic, this figure shows you the idea behind this concepts of resource or reserve. Okay, so you can have like a huge mineralization. So over this pink area, we have, for example, gold. And we're gonna make some drill cores, and every time that you see around a circle like this, you can imagine that we have over here a drill core. Okay, so we went to the field, we collect samples on those areas, and we analyze the sample. And definitely we have ore. Okay, we have gold on this point. But then we have to choose a narrow area because we're talking about kilometers area. It's too wide just to analyze everything. And on that area, or in that area, we're gonna increase our knowledge. We're gonna make more drill cores. Okay, we're gonna analyze more material. So you can imagine we're gonna spend more money. Okay, and by spending money, we're talking a lot of money, serious money, in order to have this information, this data. So we have to use this data somehow. So then we go to this darker pink area, almost reddish area over there. As you can see, we have now a regular lattice, and our drill cores are close together. Okay, but we're still talking about a difference of some meters from one point to the another, or something like tens of meters. Okay, and then we have another area, a smallest area of all, and then we concentrate everything that we have on just that area. Okay, so that's how we mine. We have an idea on how big our deposit is. Okay, but we can't spend money in order to make this like a lot of needles in our haystack. I just have like a few needles in that haystack. Okay, but in some parts of it that I know for sure that we have something that we can sell it, then we concentrate our effort. And during the time that we're extracting ore on that place, we're going to increase our knowledge around us, okay, in our surroundings. And that's why I showed you like a circular graph, okay, a circular idea at least. So come back to cogs. We go on to have always geologists working with us in the mine, not exactly where I'm taking ore out of the ground, but also around us in order to increase our knowledge and in order to decrease our risk. It's always a risk evaluation thing. Okay, so another one joining us. So let's move to the next slide. So just consider this. Okay, we have now 3 ore bodies. Okay, and they are represented in gold. Okay, so let's consider that we have 3 gold bodies. Okay, ore bodies. At the beginning, you went to the field, you performed some analysis. It could be geochemistry or geophysical analysis. It doesn't matter right now, but in the end, we're gonna make some drill cores and we come back with the results and bingo, we found something, okay? We have gold. And then we're gonna start to mine this gold. So considering that we have an underground body, we have to access the body. So the first thing that we're going to do is what? Open shafts. and this shaft is going to connect the surface to the ore body. Once we're down there, okay, we're going to start to mine this body. But as soon as we start this, we start to taking a look on more bodies. Okay, so if you have one, you could be in a place that you have more occurrences of this material, and that's exactly this case. As you can see over there, we have three. We have a big one and we have two small ones. Okay, and we won them all. That's definitely we won them all. Because of what? I always have to open two shafts. Okay, just not only for security, but also to have air circulate, air flowing between these two. Okay, so yeah, we're gonna have at least two. And if I'm gonna have to open two shafts, why not open two shafts in two odd bodies? That makes a lot of sense. And in this case, one odd body is apart from the other one, something like 3 kilometers. 3 kilometers of rock just to connect these two. But yeah, it's doable. Okay, so if we calculate and see that it's cheaper for us to make this tunnel connecting the two ore bodies instead of open another shaft, then we do it. Okay, we connect these two shafts underground. Okay, and what else? I'm going to stop. That's okay. That's this. We're going to extract this material, this gold ore, and then we finish. That's not exactly the case. We're going to be spending money. Now that we're making money, we're going to spend money in order to increase our knowledge and in order to find more bodies. And in the end, what we want is this: samples. Okay, so those are drill core samples. You can see, barely can see, but it's someone holding two drill cores. Okay, and then we're going to analyze those. So if you consider that we're in a scale of kilometers, and it's really expensive, drill our material, collect the samples, process the samples, analyze the samples, and then get to a number. Okay, because in the end, what we want are numbers. It's a lot of money and there's a lot of time and resource just in order to get these numbers, okay, or those numbers. But yes, in the end, what we want in this stage is to literally get hold on our drill core samples. And from that one, we're going to do a lot of analysis. I'm going to show you something or some possible analysis that we can do. Okay, so it makes a lot of sense for us to talk about how can we get samples. Okay, and of course, we're not going to do this with the geologist team anymore. We're not going to ask them to go to the field using something like an OG and just stay there rounding the OG in order to go down like 4,000 meters, 3,000 meters. That's not going to work. That's definitely not going to work. And the productivity of doing something like that is almost zero. What this guy is actually doing, he's probing for soil. Okay, so it's just a soil probe. And that's okay, you can use an LG to this because you're not going to drill more than like 1 meter, top 2 meters. As you can see around him, it's probably cornfield. So he just wants to take a glimpse on the surface of the soil, okay? So when we talk about mines, we're talking about things like that. Now you can see how our manual Algeria became a machine, okay? And those machines are amazing. And even today, you can go online and see a new machine. So every day is a new surprise, it's something bigger, something more robust, and something autonomous. That's quite impressive. I choose this picture in order to start all of our mechanical pictures because it's not only a drill, but it's an inclined drill, okay? So it's making this drill like 30 degrees with the horizontal line, and it's quite difficult to do this, okay? It's not easy. Just try to take a regular drill in a home and perform an inclined hole and drill it. It's like 30 degrees and you're gonna see for yourself it's not easy, okay? And yeah, the guys are doing this. So when we talk about mines, you're gonna see big things, okay? And nowadays people are paying a lot of attention on those big things because it's beautiful and you can have like a very beautiful composition. What we're seeing right now is different from the other picture because on the first one, our drill machine just have rotation. So it's just like your driller in your home. Okay, you just take it and drill. Okay, but if you try to drill in concrete, you're gonna see that rotation is not enough. You need like a hammer on it, and that's why your drill, you can just choose. You can switch between drill only and drill plus hammer. Okay, and that's why we have over here. So it's big because you have a hammer, and this hammer is going to punch the material down. Okay, and then you have two things going together. You can have the rotation plus you can have the hammer effect, and you can drill faster. Okay, definitely. And this picture is from Brazil. This is from Carajás. So if you consider there is a lot of money just to have one drill machine, consider that now we have just four in the same picture, and they're really close together. Why they are doing this, why they are drilling so close together, because they're going to blast this area. Okay, so they're going to load these drills cores with drill holes with explosives, and then we're gonna blast this area, complete blast this area. And we can do this underground too. So it's not the case of doing this overground, but also underground. As you can see in this picture, it's a very good picture. I choose this as being a very good picture because we have very different environments to work in the underground without any kind of individual protection equipments and things like that. But this picture is okay. It just have one flaw. Okay? So you can see that this guy is not drilling. It's like a model. It's just posing for the picture because we don't have water coming out from here. Okay, so when you make a drill like this, in order to protect everyone, including this guy, he doesn't have any facial protection over here, so he's breathing the air in this mine. We add water. Okay, so over these cables over here, we have two. One would be compressed air, and the second one would be water. The water is going to be flowing around over here and accumulating in here. We don't have water. So this guy, he's not actually doing it. He's just posing for the picture. But it's a beautiful picture, okay? You can see that the ceiling over here is protected. It is protected. And that's the right way to do it. Okay, we protect the ceiling. But we only protect the ceiling if we're not going to move material around the ceiling, okay? So again, this is just like a fake picture, but nevertheless, it's a good picture. And when we talk about machines, we have those machines right now. We call this jumbos. And this jumbo, you can put not just one drill, but you can go for two, and eventually you can reach 32 arms. And on the point, on the tip of every single arm, you have a drill. Okay, so we can take a look at that video over here. It's Sandvik video. And Sandvik right now, they are Sandvik Tanrock, and they are experts on those kind of machines. Okay, so let's take a quick look. And again, I'm gonna put down here in the description the links to these videos. So if the quality of the video is not okay, or even if YouTube is going to cut my video, that happens on our lecture, I'm just gonna move instantly from one point of the lecture to the other, cutting the video out, but I put on the video description where you can find this video and where you can see it for yourself and even listen to the sound. Okay, so that's how Jumbo works. And they are preparing the arms right now, and they're going to start the drill in a few seconds. Just see, it's all electric. Okay, so that's why it's really, really good to the environment to have this. So 3 meters, we can drill up to 3 meters, and we can cover an area of 6.6 by 10 meters almost. And as you can see, it's gonna do everything by itself. It's a long video, it's not too short, but Sandvik on this video, I think they got it. They just nailed it. They're going to show you everything, even as you can see, the power intake. Okay, so they present the graphic to show you where is going to be the peak, the intake, and how you can do it. And can you see how many drills they just made it? It's amazing. Because if I put a lot of explosive in just one point, what is going to happen is when I blast it, I'm gonna lose the material, or I can have chunks of the material. I can ruin our gallery, our tunnel. So yeah, we have to make a lot of drills, not like one or two. Okay, so we need big machines. And eventually we can be drilling offshore. Yeah, we can be drilling on water, and we need technology to do this. Okay, so this is a very, very beautiful picture. We're taking oil out of the sea basins, the sea floor, and we have to drill it. So in the end, it's all about materials and the materials that we're using, but we need bits for our drills that can actually withstand all of these stressful situations, and we have it. So coming back to that beautiful pictures, now we have another one. It's more feasible one, but again, I don't think the guy is actually doing it. I think at this moment he's just posing for the picture, but he's a little bit more dirty than the first one. So I would eventually believe that this guy is actually working in the mine. His light is off. Okay, he's not using any breathing equipment. There is no water over here. So yeah, I'm not entirely sure if this guy is actually a miner, but considering his pose and how he is holding the jet lag, and he is a little bit dirty over here, maybe he's doing this. But you can see the water is right here. Okay, maybe he just stopped the water flow just to take the picture, but definitely this is an active mine. Okay, it's not active where he is right now, because you can see over here that we already stopped the activities. We have equipments over there in order to secure the sailing. So I don't believe they're going to blast this wall, but nevertheless, he is there. Okay, so talking about blasts make a lot of sense about showing you guys explosives. Okay, we don't use dynamite anymore. We prefer to use different combinations. In Brazil, the favorite one would be anfo. Okay, and when we talk about this, we actually talking about two words that came together. So anfo means ammonium fuel oil. So you have diesel plus ammonium. Okay, and if you mix these two in the correct proportion, and if you pass through them an electric current, then you get yourself explosive. Okay, so you can work with anfo just like this. This is just the mixture. You can have this in a way like a sausage, because you protect your explosives inside of the cartridge. This is old. Okay, this is like TNT. This is old school. We don't have this anymore. It's not safe. Okay, but this one, it's quite okay. Okay, this dyno noble, and we have this all around us, and this is the cables that's going to connect the explosive itself with the starting device. It would be this one. Okay, and when you pass on electricity to that cable, the starter is going to make kaboom first, and then your explosives go after. But when you take a look at something like this and you're actually in the mine, I strongly recommend you to turn around like 180 degrees and run for your life, because probably we're gonna see after this is something like flying rocks. Okay, and we're gonna have this material being blasted. So guys, I like this expression a lot. I just added the source. Faith can move mountains. Okay, this is quite beautiful and profound. I strongly believe that's true. And it's Matthew 17:20. And what I want to add to this after Matthew, and Matthew was like 2,000 years ago, given or taken, it would be something like that. If faith can move mountains, imagine explosives. Okay, so explosives nowadays, we can definitely make this come true. So I'm gonna just show you guys some explosions, some blasting, and as you can see that light going on, that's our starters. Okay, they're connecting the starter, that's the electricity going there. And it's not only electricity, we can use nitropenta as an starter. It's a small explosive, but it's quite fast explosive, and that's why we connect all the explosives and then we have the blast. So this video is quite nice. I strongly recommend you to do exactly what they ask you to do, which is crank up the volume and listen to the blastings. There is a lot of emotion in seeing this. I have to tell you, I love to see this, and people from McAllen, they really know how to do it, and they know how to do it so nicely that I actually bought not one but two videos from the guys. Okay, that they have like a compilation of videos every week, and they have the best one that I love most is the month compilation. Okay, so once per month they just put one short video with everything they have done over that month, and you can see something very, very crazy. Okay, so if you see something like this is actually not a good blast. Okay, you have a lot of gases going up. We don't like this. You're actually losing energy by doing this, and you're projecting material, so that's not okay. If you take a look at the video and again to this picture, you're going to see difference. This one you have a lot of material going out, so this is just show off. Okay, you don't like this, you don't want to have this, you prefer to have things like this. Take a look at this aquarium, and this is a good blasting. Okay, so nice and easily, you don't need to show off, you don't want to put things up in the air, you just want to fragment your material, you just want to have a nice and organized pile of material, and with this pile you can work with it. This is a quite difficult thing to do, to have a blast like this in front of houses or buildings, and that one was a feat of engineering. That one was amazing. Okay, these guys are quite nice, they're very clever. As you can see over here, different areas, 3 different areas, 2 different mine points, and they just blast together. So this one is not so good. Okay, but the other ones, yes, they are on the top. Okay, so after that blasting and the blasting moment, that rush of adrenaline, we exploded everything. Yes, what we're gonna do is taking the material out. Okay, so the next stage is going to be all about logistics. Okay, so we have to now load the material and send it away, and then we have our dinosaurs coming. Okay, so if you see these 3 letters over there, CAT, cat, okay, that doesn't stand for the animal, that stands for those dinosaurs over there, and those very, very beautiful machines. Okay, so this actually stands for caterpillar. Okay, that's because of the wheel system. They don't use wheel actually, but they use this kind of system, so they actually correlate with the insect caterpillar. Okay, and nowadays they're just cat, and they can move a lot of material in a very narrow time. As you can see in this video, Caterpillar is not only about loaders, they can, or excavators, they also produce the trucks, and they go together very nicely. Okay, because they are all uh, designed to work together, so everything fits in the right place. This is also a big picture, a big video, sorry. The footage have like 10 minutes, but if we take a look at this, you can see a cycle of load the truck, move the truck, and another truck arriving. And this is quite important for us because, as you can see, everything is just in time. Okay, so everything here is about logistics. It's really expensive to leave that truck stop where it is, okay, because we're spending money. The engine is on. Okay, it's not like a car in the Europe that we just stop on the traffic lights and the engines goes off. Engine's still on. Okay, as you can see over there, that other truck going down, it is not taking actually ore. So if I'm moving ore, I'm also moving overburden, and I'm moving material that's not ore itself. Okay, and yes, sometimes we have to move more material, waste material, than we have to move ore. That's actually normal. Now we have another shadow approaching. Okay, and that's the next truck. As you can see over there, we have in our place, we have the capability to feed 2 trucks, not simultaneously, but we just finished one, and the operator are going now to clean the area because another truck is going to arrive over there, but it can move 180 degrees. No, it can move 360 degrees around, and we start the cycle with the other truck. Okay, so we clean one of our benchworks, let's say something like that, and we continue mining our ore. Okay, and that's pretty much what we're going to do 24 hours per day, 7 days per week, 365 days per year. Okay, and another truck is already arriving. So everything is just in time, people. And this material, it's going to be delivered directly to our mineral processing plant. So if one of these links breaks, everything is going to stop. Okay, and we can't afford to run out of ore in our mineral processing plant. We just can't. Okay, the mill can't be empty. That's not thinkable. Okay, we have to have ore all the time, and that's why we're not a chain. Definitely, we're not a chain. We're cogs. You can see right now one cog is moving out. Okay, he already horn. He give the signal. Okay, I'm moving because there is another truck arriving. Okay, and the other truck is already there. As you can see, they are not actually quite synchronized. They have a small delay right now, but they are operating quite nice. The guy know exactly where to stop and when to arrive because we have also the computer helping us. We have GPS in all the machines, so we know exactly where we're taking ore out from and where we're going to deliver this ore and when we should be delivering this ore. So again, another truck, and take a look. They pass so close at each other, like centimeters from one to another, and they can do this. And we definitely can have some accidents, and one machine can actually scratch the other, but that's nothing that we can not work around it. And as you can see, this caterpillar is quite new, so no damage at all up to today, or to the day that we make this footage. Okay, so let's move on. Okay, and if we're gonna be showing you guys equipments and big equipments, we'll be staying here the whole day because we have so many beautiful pictures. And again, not only excavator but loaders, and we'd be looking at this for the whole day. And this is standard in Brazil. Okay, people in Brazil, they love caterpillar. Okay, we have other branches in Brazil, but caterpillar would be the top one. And this picture is also coming from Carajás. I'm going to mention the name of the guy who took all of those Carajás beautiful picture is actually a Vale employee, and he's an amazing photographer. Okay, so you can feel free to follow the guys on the social media or on the LinkedIn. You're gonna love his pictures. And this is again another picture from this guy. Okay, and also this one. Okay, as you can see, we work not only with daylight, but we also need to work over the night, and we do it. Okay, so we work like 3 shifts every time. Okay, and you don't need to have just one supplier machine. You can be working with Caterpillar, but you can also use like Komatsu, Electra House, Haupak, and you can put all of those together. But then again, if you have to keep spare parts for many different machines, we're going to require you a lot of money and even a lot of space, and you're going to end up having a lot of trouble. But I put this picture not only to show you that we can have different machines. It's not the case of having different manufacturers. It's all Caterpillar in the picture, but we have different Caterpillar machines. But we can also take a look at this guy over here. This is quite interesting because this is our GPS relay tower. Okay, how can I know for sure that we're going to be taking ore for the right position? Because we have GPS for this. And this picture over here, it's impressive, it's amazing, not because of the GPS tower alone, not because of the Caterpillar equipment alone, but because on the 7th of May this year, Caterpillar achieved an amazing feature. They actually sum up 3 billion tons of material hauled using only autonomous command tracks, as you can see over here. So this is a driveless system. We don't have anyone in here or in here driving the truck. Okay, the truck drives itself. This is an amazing feature. Definitely, this is amazing. Okay, so when we talk about space mining, the first thing that people consider is how are you going to live over there? We're not. That's the beautiful of it. Okay, we're not gonna be there. We're gonna be sitting here, and the machines are gonna be there, and they're gonna be doing all the fun and hard work for us. Okay, so we don't need people anymore to drive trucks. We can let the computer do it. And Google proved to all of us, okay, that you don't need a driver anymore. The car can drive itself. And eventually, the car can learn from the driving experience. And one thing funny is Google Driver was a worse driver in the end of the experience than what it was in the beginning of the experience. This is amazing because this happens with us. When you start driving, you're a bad driver. After a few years, you become a very good, a very skillful driver. Then you're gonna become old and you become again a lousy driver, a bad driver. And that exactly thing happened with Google Driver. Okay, why? Because the car started to learn how the life itself it is, and we're not good drivers. So he started to drive as we do. Okay, and by doing this, he became automatically a best driver in his concept, which would be a worst driver. Okay, all things considered. And again, I think it's amazing to see pictures like this. Not because you have nature on your left-hand side, but because you're actually in a mine and you're putting everything together. Okay, you're doing mining. Okay, you're producing. You're making money. You have all of your trucks going together. It's an amazing picture. Definitely consider the amount of material that are moving, and you can see that everything is actually clean. It's quite difficult to keep the trucks clean like that. Okay, but we can do it. And you can have amazing pictures. Just this one again, it's one of the kind. So if you consider what would be driving a truck like that, I can tell you for sure that it's an amazing experience. I never drive one myself, but I've been quite close, and you have an amazing view of everything in the mine. Okay, not on your here side, of course, it's too high, but you have a very beautiful view. So I brought you another video, and this video is going to show you some machines. So this is a Hitachi, and it is a 2,700 HP motor. It's amazing. As you can see over here, they have to install a stairway so to allow people to safely go up, and it's really high. Okay, and you can actually transport something like 300 tons of material in just one truck. Okay, and this kind of conference, they're amazing. Okay, in United States they have this every year, and Canada also. I'm not sure about Africa, and in Brazil we had one, but nowadays because of the COVID, it's not trendy anymore, of course. And we hope that in the next couple of years we can come back and see this. But as you can see over there, the payload is 300 tons approximately, and is an amazing engineering feature to develop a machine like that and to build a machine so big like that. But that's not the biggest one. Okay, it's just for you guys to take a look what we can have. And if people from the agronomy, the agro engineering, if they like that the equipments, if they like that feeling of have a big machine around them, they don't have a glimpse of what we have on mining. Okay? Yeah. Nowadays we're very well equipped. I can tell you for sure. Again, it's not a short video, but it's going to show you some different machines. I think it's worth the time. And you guys are going to understand after that why I'm showing you these different equipments, because I'm going to connect two different videos. Okay, so the end of this one is going to begin the beginning of the next one. So take a look at the axis and the tires. If you want to order something quite expensive, you can consider a truck like this. If you want to show off like a monster truck, take a look at those. Okay, so this is the Liberher. There's a German one, is the T284, and now you can see it moving. It's quite nice. I think it draws a lot of attention. If you want to take one of those to to spin it around your city, I think you're going to be in trouble to find a place that you can actually drive it. But nevertheless, would be a quite experience, like Michael Bay Transformers experience. So after you put it in the conference room, it makes a lot of impact, literally. Oh, guys, this tire, it was a lot of money, literally. It was a lot of money. And this guy, this bad boy, can transport 400 tons. Okay, so the payload is 400 tons. And when you talk about drones, we're talking about a few grams payload. Okay, and those guys, they can transport 400. So maybe in the future, people, we're going to be moving away from this kind of trucks and have like a swarm of small drones. Can happen. Okay, if we see that it's more environmentally friendly to have a swarm of drones delivering material instead of transporting something like this. But if you consider what we're doing right now, we always have this idea that if you can put more material in a bigger machine, it's going to be cheaper. And we do this not only for trucks or for loaders, we also do this for airplanes. Okay, and so far it's working. The number that you're seeing over there, 97, that's the amount of material that you have on your, it's your payload on your truck, loaded on your truck. So it have a weight on it. So this is quite good because of what? It's going to allow the guy who is actually operating the excavator to see how much material you already have and how much material you can still put on it. Okay, so you take a look, and over there it's almost 400, so you have to finish. You can put more material. It's quite clever. It's quite clever way to deliver information from one guy to another. So you can see that the guy, it's really scared to pilot the truck. Okay, so drive right the truck, because if he makes something wrong, everything can come down on top of them. Okay, yeah, it's quite a nice machine. Okay, let me just move forward a little bit in this part of the video. Okay, they spend a lot of time on this lever. Let me move away for another one. Okay, so this one is a Komatsu, another big one. Okay, and again another conference, and now it's going to weigh 380 tons loaded. The payload is going to be the same. It's like standard around 300 tons. They're going to show you, but you can see how we can access the pilot stage. Okay, 327 tons. Okay, Komatsu is also very common in Brazil. You can find many Komatsu's equipments around our country. Let's move to another one. So this one is a Caterpillar truck. Okay, we already saw those guys in action. I'm just gonna show you a little bit how you can actually go near it, and everybody wants to go to the cockpit. That definitely everybody wants to get there, even stay together with the tires and take pictures, because it's really beautiful, definitely. But I just want to show you guys how you can take a better glimpse. It's really high. But I'm going to show you guys this last truck over here. So this truck is not actually common in Brazil, because there's a Russian manufacturing company, okay, Belas, and you can see that they're quite strange trucks if you take a look at the bucket, and because the truck itself is like narrow. Okay, so when you take a look at this, you know, but you can put a lot of ore in that, because this truck is actually designed to transport high density material. Okay, and by transporting this high dense material, that's the second video that I mentioned to you, you don't need a very big trunk. Okay, if you just do it, you're gonna use not wisely the weight of the machine itself, because you're gonna have a lot of steel and you're not gonna have use for this steel. As you can see, we have different manufacturers in this company, this mine company. So this is a real footage of a mine. So you can see the excavator down there, and they are delivering materials to this truck, and then the ballast is gonna go there, and it's gonna be loaded, and then the transportation starts. So as you can see over here, not a good scenario. We have more trucks than we should, but you can see the drillers on the top of our slope. You can see the tractor over there, and it's a loaded the loader. They just pile everything together. It's just making the maintenance and the cleaning stage. And then you can see the cycle of having the truck loaded and another one coming to the same position to load it and to leave. So at the time they're performing this footage, they were working with this equipment. They are actually evaluating the performance of those node trucks coming from Bellas. Okay? And they succeeded, they passed the test. Okay, so P&H is also a very common manufacturer company for these big machines in Brazil. So when you talk about excavators, PH is also a reference in all the world, but in the mining world, they are also top 5, one of the most important ones. It's quite nice how the truck can hold all the weight, and you can see they have a scale on its side, but it's not showing any number. It's just a 0. Now it's showing the number 8 over there, but I don't think it's correct. Oh, now it's moving. Yeah. So let's move forward because we already saw a lot of trucks. Okay. So what now? Now we go to the mineral processing itself. Okay. So we already know that I need to take a look at the ore, the quality of the ore. When I say grade, you're going to understand in a few slides what I mean by that. But now I have to deliver the material to the mineral processing plant, and that's why we have those kind of field. Okay, so now you can see the name of the photographer that I mentioned to you. His name is Amarildo. Okay, so if you go on LinkedIn, Amarildo Fotografia, you're gonna find it. It's like Amarildo photographer, and you can see his amazing pictures. This is just one of them. This is actually Carajás again. We have like 3 mineral processing plants together, and we're gonna take a look deep into that. Okay, but before we started this, I didn't show you guys any books in order that allowed you to read and to increase your knowledge. So I'm going to start with this book coming from 2 professors that I'm very pleased to say that I know the guys. So this book, it has the author's name on it, Wills. So Barry is doing an amazing job over the last few decades handling this book. Okay, so from time to time we have a new edition of this book, and he always invited another author to be with him. So this is the 8th edition, and this one it was written not only by Wills but also by Jim Finch. Okay, so everyone who knows a little bit about flotation and column flotation, they know the name Finch. Okay, even because they have another book only on flotation, and I'm going to show this book in the future. Dobe and Finch, they came together and wrote the book, but Jim is another name, very strong name in mineral processing. Everybody knows it. He's retired right now. They both retired right now. There's a video on that, but nevertheless they left us this amazing legacy. So if you want to have a book in order to allow you to better understand mineral processing, go for this one. Okay, in my opinion, it's a very starter book. You can read it and you can instantly understand almost everything that is in the book. So if you finish a chapter and you don't understand something that you read in there, or if you go further on the subject, after every chapter you have a list of more reference that you can go for it, and you can browse and you can increase your knowledge. So I'm going to draw a lot of things on this lecture from this book. Okay, and I'm going to show you where I'm going to be using the book, but definitely this one you should consider. Okay, so another book that is also quite nice is the Gupta and Ian book. Okay, so two professors again, and this book, it's around for a couple of years. This one, the second edition, is from 5 years ago, but then again, it's a very, very good book, and I think it's a little bit more complex than the first one. Okay, but if you have any previous contact with mineral processing, you can browse the book without many problems. But one thing that you're not gonna find on the first one is dimensioning. Okay, you're not gonna find a lot of math equations. But if you're more interested in dimensioning your equipments and math itself, and physics itself, you should not go to the first one. Probably this one, mineral processing, design and operations, you're gonna have more things to allow you to better make your calculations. Okay, that's another book that I like a lot. It's from Zilmaya, and Ian, he makes a very good thing translating this book, because this book is not the first edition of it, it's the first English edition. Okay, so Professor Ian, he is also around for a few years, and I'm not going to tell this guy's age, but you can figure it yourself. You can just go online and take a look. They are our support pillars. Okay, they are our mentors, and this book, I think they have like 4 editions in their native language, and then he came with this English translation, and it's like a jewel. Okay, you can find this book. Normally, mining books are not cheap. Okay, so you're gonna find books like $100, $180. I think because we're so few that the authors doesn't make any profit selling books, so they're gonna sell like 5 books in the lifetime. So you're gonna have to pay a lot of money because they're gonna sell like only 5 books. Okay, so they have to have some profit. But nevertheless, take a look at the books. Even on Google Books, you can read part of the books, and you're gonna like it. Okay, this is a free one. Okay, so if you go on this website that I put on the bottom, you can take this material, this Metsu handbooks. Now it's Metsu Autotech, but nevertheless, you can get those books for free. Okay, so this basics in mineral processing, it's quite nice because it's going to give you an overview on mineral processing, and then you have crushing handbook from Metsu. I was just trying to translate correctly the name of the book, but I think it's Metsu Crushing Handbook, or Handbook in Crushing, something like that. It's also a free available ebook for you, and they also have a printed version of these booklets, but you can have it for free, and probably it's going to be available in your language. I know for sure that we have all of those books in Portuguese. Okay, just go on Metsu website, go to the Portuguese version, and you're gonna find it. Okay, and it's quite good. It's really quite good. And since they're a company, they're not interested on selling books, so those books are for free. Okay, you can just go there, and you can use in your lectures also. Okay, it's freely available for you. And I like very much this book. It's coming from Maurice Fustenot. So Professor Fustenot, it's an American professor. I had the pleasure to attend the SME conference, the last SME conference in Denver, Colorado. It was 2 years ago. Yeah, it was 2019. So everyone was there, James Finch, Wills, everyone, and we're celebrating the first 19th anniversary. So we have a very good dinner. Everybody was together, and Professor Fustenot and his wife also attended the dinner. So if you want to take a look on how mineral processes have been done over the last 50 years, I would say, take a look at this book. Okay, so these principles of mineral processing, it's an amazing book, and you're going to see a lot of compilations coming not from other books only or from other papers, but also draw for their own experience. So Professor Fustenot and Professor Han, they made a lot and lots and lots of tests with many different ores, not only for the United States of America. So yeah, go for this book if you want to have a more inside view of mineral processing in the United States. Another USA book is this one coming from Professor King, Peter King. Unfortunately, Peter King is not with us anymore, but as you can see, there is 2 editors more in this book. So the second edition of this book was actually put it together by his former student, Claudio Schneider. He is a Brazilian researcher. And actually, Peter King's widow helped with this the second edition. It's Ellen. That's why you can see two King names in this book. But if you want to do modeling and simulation, take a look at this book. Okay, they try to compile everything and every model that's around and that can enhance your models. Okay, it doesn't matter if you're going to use like artificial network, if you're going to use Monte Carlo simulation, that doesn't matter, because in the end of the day you need equations, and this book have those equations. Okay, so take a look at this. I think you're going to be surprised. It's a very good book, but it's not a book that's going to introduce you to mineral processing, definitely. Okay, so you're in a different level, go for this book. Okay, and if you're in the beginner level, I would strongly suggest to start with wheels. And I didn't introduce the Sitem book over here. It's free. Okay, it's easy to download. You just go there and download it. It's open source, but it is in Portuguese. And since this course should be held in English, I'm not going to show you guys the book right now, but I'm going to show you this book cover in the end of this lecture, or probably in the beginning of the other one. Okay, so if you want to find a Portuguese book, we have two books that you should be taking a look. One is just one volume, it's the Sitem main book, and the second one is the Professor Arthur Pinto Chaves collection. Okay, he has 6 books on his collection, and definitely it's something that you should take a look at it, but it's going to be in Portuguese. So if you can't read Portuguese, stay on this list that I'm showing you today. Okay, and then we have to have some definitions in our hand. Okay, and the first definition is mineral. So I'm talking about a lot of mineral processing, mineral this, mineral transportation. What is mineral? Okay, and on the very first pages of Will's book, he's going to come with this definition of minerals. And this definition is actually a geological definition of mineral, and it's a natural inorganic substance that has a chemical composition and atomic structure well defined. Okay, has to be well defined. So if you're talking about synthetic gems or synthetic minerals, they're not mineral. First thing. Okay, so if you talk about synthetic diamond, it's not a mineral. If you have something in your hands, like I have in here, in the end of the acidulation process, we have minerals, and we have to concentrate those minerals. In here, we have monazite, and it's a secondary mineral. So it wasn't there before the acidulation. So after I attack that mineral assembly with sulfuric acid, I synthesize monazite. It's not monazite itself. Okay, so if it's not natural, it's not mineral. So if it's not inorganic, it's not mineral. Oh, how about petroleum? It's not mineral. Okay, so mineral oil, it's inorganic? No, it's not mineral. Okay, and it has to be solid. Okay, it has to be solid. It doesn't have the solid word in our block, in our definition block, but normally it comes with it. Okay, it goes without saying. We're dealing with solid material. And about that chemical composition, it's tricky, because normally we have solid solutions in our minerals, and we have a lot of this kind of solid solutions. And then a chemistry came to me once and said, okay, you're saying that mineral has to have a chemical composition well defined, but you don't know the chemical composition of your material. Is that right? I said, yes. I don't know exactly the chemical composition, but I have an idea about it, so you should change your definition. I said, yeah. Nowadays, he's completely right, and I think we should change this definition to something like a well-established chemical composition, because it's not a well-defined one. Okay, but about the atomic structure, that's true. We have to be able to perform an XRD, okay, which means the X-ray diffraction, and not only X-ray fluorescence of our material, and got those results. Okay, so I'm telling you this characterization names, these machine names, because when I show pictures like this, and when I come with definitions exactly like that. People always ask me, oh, so you're talking about XRF and XRD. XRD, definitely, okay, but that's not the only technique, the solo technique to have atomic structure, but that's one of those, probably the most important one. But when you talk about XRF, it's great, it's amazing. We perform a lot of XRF in our laboratory, but we do love ICP too, okay? So ICP can also give you very good information, very solid information, and information that you can have, or at least you can have easily using fluorescence, okay? So plasma, it's a very good technique also, okay? So what else? OR, okay? OR is something that we have to have in mind what that means. So you have something naturally, and you have naturally occurring a mineral. We know that from the previous definition. And now we have something in our mineral assembly that we can sell it. Okay, so we have to have something with market value. And normally we talk about metal. Okay, and what I want to produce is a metal. I can have this word being used. Okay, and in Brazil we use ore for everything. Okay? Oh, I'm producing carbon concentrate. What kind of carbonate concentrate you're producing? Oh, carbonate. Sorry, calcium carbonate concentrate. Okay, so you're producing lime. Yes, I'm producing lime, and I have lime ore. Yeah, that's definitely not the ore definition. Okay, lime is not an ore, but sometimes you can have people using the term ore for everything that it's mineral. Okay, or it's a rock, and you're going to produce this. So if you're selling this, they're going to use the name ore. That's not exactly how you should be doing this. Okay, and that's why I put a quartz crystal in this picture, because if you consider quartz, it's an ore or it isn't an ore. Okay, do you have a metal in it? If the answer is yes, and you can sell this metal, then definitely it's an ore. If not, I would suggest you to go very carefully with the use of the word ore, because sometimes people are going to use it, and sometimes people are not going to use this, and they're going to be actually a little bit angry if you come with this and said, "Oh, I have ore." Okay, and I learned this the worst way possible, because I was starting my international career, traveling abroad and talking to people, and I made a silly mistake of saying something like apatite ore. And the guy came to me and said, "No, you don't have apatite ore, because apatite is going to be used to produce what? Phosphorus." Okay, so you don't say apatite ore, you say phosphate rock. Okay, and I'm just giving you the short version of our discussion. And after that, I said, okay, I have to be extra careful on how I'm going to use these terms. Okay, so if it is a technical term, take a look at this, and I would suggest you to go online using Google, for example, and type in the term that you want to search for, and then you're going to see that probably is not the best way to just literally translate this term from your language to English, because people are not going to understand you. And one thing that I learned also, the worst way possible, was about people don't understanding one or two words that you're saying. Okay, and in Brazil it's quite common for me, if you're saying like a lot of sentence, and if I miss one or two words, I'm okay. I'm not going to focus my attention on those words. But then I was talking to a guy, to a professor from the UK, and he told me, no, but I'm not like that. In the UK, we're not like that. So if you say just like one word that I can't understand, I'm going to stop listening to you, and I'm going to start to think, like, what he mentioned with this word? Because he never came across with this word, and he's going to start to think about that word that he can't understand. Okay, and he's going to stop to listen to you. Okay, so try not to do it. Okay? If you're gonna show a term, and it's a technical term or scientific term, take a look if the term is correct. Okay, otherwise it can be in a difficult situation. So guys, for the very first time, I'm going to show you some math. Okay, it's important for us. And then we're going to have like a quick break after this example. Okay, this is one thing that I want you guys to try to solve yourself. Okay, so first thing is, let's consider a given tin concentration, tin ore, okay, and we have just 2% of this ore, of this mineral of tin in our ore. What is actually the concentration of cassiterite? Cassiterite is the mineral bearing tin, okay? So its chemical formula, it's quite simple, is a tin dioxide. And if I come to you and said, okay, I have an ore in my hand and I have tin minerals or tin bearing minerals, one of those is cassiterite, and I have just 2% of my ore. How much cassiterite I have in my hand? Okay, and I know it's simple. It's simple. It's just having step one, how much tin I have in a cassiterite. Okay, best case scenario, how much tin do I have? And I can take a look at this where there are many websites, okay, that you can just go and browse for the mineral. And I'm gonna do this with you right now so you can take a look. And that's why I'm going to stop a little bit this screen and I'm going to change to another one. And since I'm using Google Meet, I have actually to stop my presentation and start a new one. I can just switch the coin. Okay, so just 1 second. And now you can see over here, and I'm going to move my screen here so I can actually take a look at you and do it the same over here. So I just went on Google and type in cassiterite, and it's amazing because you have 150 million results in just 0.56 seconds. Okay, and you can take a look all over here. So which one I'm going to choose? I have over a million possibilities to go on and solve my problem. I would suggest you to go in this one, mine that data, or the one that I like most. So I'm going to show you two websites, but I prefer this one, Web Mineral. Okay, for me it's more simple to browse Web Mineral because they give me what I want straight. Okay, so that's what I want. Okay, the chemical composition, it's the first thing you're going to see. Okay, so many thanks to people who actually develop and maintain Web Mineral. Okay, you're doing an amazing job. Please continue. Okay, and keep the website ongoing. But here you can see the chemical composition, the chemical formula. Okay, then you can see the molecular weight. Oh, this number, yeah, I already showed this number. It's exactly the same number. We're going to need this number. Okay, and you can see already here you have 78.77% of tin and just 21.23% of oxygen. So if you consider this mixture, you have 100% of the mixture. But why they are mentioned this to me? That's quite important to understand this. And I'm going to browse later on another mineral, and you're going to have more information about this. But just consider this. You collect a sample of your material and you send to the lab. And they're going to perform an XRF, okay, fluorescence of your material. So the XRF result is going to be all about oxides. So you're not going to have an XRF result with just tin. It's going to be tin dioxide. Okay, so you have to read this and make your calculations. So if you take the same sample and send it to ICP, of course the results are going to be different because there are different machines. Even in the same machine, the results are going to be always different because it's a different sample. I know all of that. Okay, but let's consider that I have an homogeneous material and I make a very, very amazing work in having a mass split to have two twin samples, and I send those samples to our lab and so on. Okay, but when the result come back from the ICP, I'm not going to have oxygen. Okay, there's no oxygen on it. You're going to have just the chemical element. So if you have two samples, identical samples, coming from one X-ray fluorescence and two ICP, it doesn't matter if it's a MS or OAS, it's just an ICP. Okay, the first one is going to be on oxide. Okay, and the second one is going to be all about chemical composition on elemental chemical composition basis. Okay, and another thing, if I send a sulfate, not an oxide mineral, to XRF, he's going to give me as a result oxide. Okay, so that's why it's important for me to have the oxide composition and also the element composition. Okay, keep that in mind. I'm going to show you later on a more complex mineral, and then you're going to see why this is quite important. We're going to browse apatite in a few seconds. So everything that I have over here, it's quite nice, but it's more for geologists. But if you want to take a look at the crystallography, why in the name of God I'm going to take a look at crystallography? Because of XRD. Okay, so if I perform an XRD, I need to take a look at crystallography because I'm talking about crystal structure or crystalline structure. Okay, so it's pretty much the two first things. Okay, if I'm keep on browsing, we're going to have physical properties, optical properties, and so on and so on. So I don't need those. Okay, I definitely don't need those on my daily basis. Just the first two, the very first two information. Sorry, the second one is a picture, but the first two informations, it's everything that I need. Okay, so I'm going to come back and I'm going to show you now the mean data. Okay, so when I go to mean data, it's this one. There's going to be almost the same, but the first thing that I'm going to talk is a little bit about cassiterite, about the mineral. Okay, oh, it's a rutile group mineral. Yeah, it's quite nice, but I don't want to have this information. I don't want to know about luster, about hardness, and I have to keep browsing. And then I have the classification, the HANA classification on the geology. Then I have how to pronunciate the name. It's quite important how to pronunciate the mineral name. Okay, that's great. It's Australian pronunciation, but what is the chemical composition? And then I have physical properties, then optical properties. Then I have the chemical formula, okay? And the common impurities are showing up right here, and that's something that's nicer than we have from the other one. I do like this information coming from mineral data, because when I perform the ICP, I'm gonna have those guys in my hand. I'm gonna see thallium, niobium, but where this niobium is coming from? It's coming from cassiterite, okay? And I'm not gonna have those because those are trace elements on my XRF, okay? So you perform just an XRF, the oxides are going to close in 100% and you don't have trace elements. But if you go to mean data, you can see the probable chemical trace that you're gonna have over there. Then you have crystallography. Then you have crystallography formula. You can see over here that we didn't have this on the other website. And you can even take a look on the 3D models over here. You can change the 3D models, okay? And it's quite nice if you're understanding this. So go ahead and browse it and play with that. You can have this on mineral data only. Then you have to crystal structure in the way that we didn't have before. So as you can see, that's why mean data is the top search in the Google. They have many things that we don't have on the other one, okay? And what else? You have XRD. You have the XRD of the material right over here, and you can just change the data set, and you can take a look if you have major difference, okay? But then again, where is my chemical composition? I want to get to my chemical composition. I want to make the calculations about grades, and I didn't have yet the result. So as you can see, they have many information. Even this map that shows where you can find cassiterite around the world, but they don't have the result that they want, okay? It is an amazing website, don't get me wrong, and many thanks for people who's actually maintain mean data, okay? It's amazing job. But then again, what I need right now is these numbers over here. So for me, it's easier just to go here and to collect this number. Okay, what I need is this number over here. So let's go back to my presentation and then see why I need those numbers. Okay, the number, it's right there available to us, but we don't have the ore grade yet. So let's go back. Oh, here it is. Okay, so please, someone, go ahead. Just you raise your hand. Go ahead, please.
Can you repeat the example example of apatite and phosphor when you was talking about ore. Can you repeat
Yes,
it, please?
of course I can do it. Just a second, I'm go back to my tab. Okay, so cassiterite, let's go back. So as you can see over here, it's a quite easy chemical formula. It's just tin dioxide. So let's go to apatite. It's right here. So I'm gonna take a look first on web mineral, and as you can see, it's not on the top results. Okay, so in order to allow me to get to the web mineral, I'm gonna take this one. As you can see, I already typed it because Google is not giving me this. So it's like here, apatite on web mineral or at web mineral. Oh, it's not very nicely. Let me do this. Okay, so as you can see over here, it's a more complex mineral. Okay, we have this solid solution on this mineral, but definitely we have calcium. All apatite have calcium, and we have phosphorus, PO4. Okay, and we can have hydroxide apatite, we can have fluorapatite, and we can have chlorine apatite. And that's why we always talk about apatite family and not apatite itself. Okay, let's take a look about calcium. We have something like 40% of calcium. We have only 18% of phosphorus, and we have hydrogen, we have chlorine, or we could have chlorine. Definitely we have oxygen, like 40%, and we could have fluorine. Okay, and then I took my sample and sent my sample to XRF analyze, and they come back to me and said, okay, you have 55% of calcium oxide. I said, okay, but I don't have calcium oxide. You do. It's because of the machine. The machine is going to give you this report, and it's going to give you not PO4, but it's going to give you P2O5. So it's quite common, Ramon. When you're talking with someone about apatite, he's going to come to you and say, oh, our P2O5 grades in the mine is this. And then the chemical guy can come and say, you don't have P2O5. No, I do have P2O5. No, you don't have P2O5. You have PO4. So this is actually a very, I'm not sure how to put this in an adjective. I would say nasty discussion, because actually you have PO4. But your machine is going to analyze for you P2O5, okay? And you're not gonna have water in your result, okay? XRF is not gonna give you water. So probably if you have hydroxyapatite, you're never gonna know it if you only analyze using fluorescence, okay? And I know for sure that when I try to analyze chlorine, you're gonna fail also. So you have hydroxyapatite or chlorine apatite, you're not gonna know it. Not using XRF. If you're using XRD, maybe you can have this glimpse, but if you perform an ICP, then you can narrow your results and okay, I have this amount of chlorine, and this chlorine is coming from the apatite. But fluorine, you can came with fluorine, okay, XRF can give you this number, okay, so fluorine apatite you can actually trace, chlorine apatite and hydroxyapatite you just can't, okay, but definitely you can know for sure how much apatite you have. Okay,
Thank you.
not at all. Okay, so again, let's come back, and if we come back again, and if you go to mean data, okay, they're gonna have more things about apatite over there. They have beautiful pictures, fluorapatite, and in here just fluorapatite. But if you browse, I'm not sure why my internet just stopped loading. Let me refresh this. Okay, it's not working, but they have. Oh, now we do have it. As you can see, it comes with different colors, which is not quite nice to see. But for us, it doesn't matter because we're going to mill everything down. Let me go down. That's the apatite name, family name. So as you can see, we have igneous rock, sedimentary rock, and that's why it's quite different. Talk about apatite production in Brazil of phosphate rock production in Brazil and when you talk about phosphate rock production in Africa, okay, with different situations over here. And this one over here, it's quite important for us, Nelsonite, because our niobium, it's right in this rock. Okay, so this is all about Brazil. And if we keep going down, as I mentioned to you guys before, I can see where I can find apatite in the globe. Okay. So yeah, mean data, it's quite nice. I like the website, and if I may suggest you browse both. Okay, you're not gonna find conflicting information, but you're gonna find additional information if you take a look at both websites. Okay? Again, it's completely free and available to you. You can just go there and knock yourself out. Okay. So what we did right now was we collect the number of the molar mass of tin and the molar mass of oxygen. You have done this many times before, guys. I think you do this since high school, so that's nothing new for you. But then we can evaluate how much tin I have on the cassiterite and on the pure cassiterite. And it's the same number that I showed you guys before, almost 79%. Okay, so this is the stoichiometry. Okay, so this is the perfect crystal of cassiterite. So the step 2 is like make just a correlation between pure cassiterite and my cassiterite ore, or my tin ore. So if I have 2% of cassiterite over a universe of 78.8%, which is possible to have on this mineral, how much mineral do I have? I have only 2.54% of mineral in my ore, on my zinc dioxide. So guys, here we have to talk a little bit about these conversions and understand something. This is quite different from one mine to another. Okay, so if you come here in Catalan and if you went to the niobium mine, if you start to talk about the grades with the guys over there, they're going to talk to you about niobium grades. Okay, and they're going to come to you and say, oh, our niobium cutoff grade, what is the cutoff? Is the grade that I'm going to choose the blocks, the mineral blocks in my mine to say, oh, this goes to mineral plants and this not going to the mineral processing plant. So that's the cutoff grade. Okay, so let's fix a number right now, just an example number, like 1.5%. If I have more than 1.5% of niobium, this is actually a ore block. So this is ore, let's go to mineral processing plant. So if it's below this threshold, if it is below 1.5%, it's not an ore. Okay, at least I don't consider this an ore. This material goes straight to the waste pile or to the waste heap. Okay, so now let's make this differentiation. We have the tailings then, okay, and later on we're going to talk about the tailings, but we have also the waste heap. Okay, so this material goes to the waste heap. Okay, overburden also goes to the waste heap. And then they're going to continue talking with you about niobium grade in percentage. Okay, but they actually talking about niobium pentoxide. So they are talking about NB2O5, because every single analysis they perform over there, it's XRF, it's fluorescence. Okay, and they talk daily on oxygen basis. And in Brazil, we like to make things short, so we just reduce everything. And they think that, and when I say they, I think all the mining people, they think that NB2O5 is too big. They just go and say niobium. Okay, so when they say niobium, they want to refer to NB2O5, but that can be tricky, because if you don't understand this, if you don't know this, you're gonna think, well, it's quite good. Or because if they have 1.5% of niobium, just imagine how much niobium pentoxide they have. Then imagine how much mineral bearing this niobium they have. So the mine, it's quite rich, and that's not the case. Okay, that's not the case. They're not talking about niobium pentoxide. They're talking about niobium, but referring to niobium pentoxide. Okay, and that's going to also work with iron ore. Okay, and iron ore, it's even worse, because sometimes you get to a place and the guy give you this number. Oh, our grades over here, iron grades is 60%. And you come and said, oh my God, now I'm confused because 6% is a number that could be related to iron oxide or only iron. And now I'm not sure if you mentioned one or the another. So which one of these two you're actually referring to? Okay, because the highest grade that I can have, talking about iron, is 68.8% or something like that, 69%. Okay, that's the top that we can have, like we're calculating, evaluating over here. So if you say something like 60, you could have both. Okay, both agree with this number. And then for most amazing thing that it could sound, normally people talk about iron oxide as just iron grade. But I went to one mine company 2 years ago. It's an Anglo-American company here in Brazil, and they were talking about iron, and they, out of the blue, they mentioned the number 40%. I said, 40%? I said, yes, our iron content here is 40%. I said, okay, now you added the adjective that I want to hear, content. Okay, so if you come with this word over here, content, you're talking about the chemical element, not the oxide. Okay, so if you come to some place and said, oh, my niobium content is 1.5%, you're making a mistake. You're wrong. You're fundamentally wrong, because 1.5% would be for us a very good block of ore, chunk of ore, percent of niobium pentoxide. Okay, so please keep that in mind, because this can be confusing. Okay, and sometimes can mislead you to different results on what do you actually want. And that's why we go to our second example. Okay, it is also coming from the Wheels book. And now let's make things a little bit more complicated, guys. Okay, so now consider this. You have three phases, okay, three mineral phases. We have chalcopyrite or chalcopyrite, depends on where are you in the globe. You can say chalcopyrite or you can say chalcopyrite. Okay, so chalcopyrite, pyrite, and sulfite. Okay, so this other sulfite, non-sulfites, sorry, is the other minerals that actually contain copper and iron, but they are not sulfites. Okay, so we have two sulfites. And then we analyze, okay, and we know that the concentration of copper in our material is 22.5%. Okay, we have 22.5 copper. And we have a concentration of 25.6% of iron. Okay, so I want to know how much pyrite I have and how much non-sulfite I have. Okay, so learning how to do these calculations are quite important, because we need to know how to tackle this material in our mineral processing plant. We have three phases, at least three phases. Two mineral phases we know for sure what they mean, and we have it down. So chalcopyrite, pyrite, and the other phase we don't know what we have on our hands. Okay, so how can we do this? First of all, we need to know geology. We need to take a look which minerals is going to contain copper and which minerals are going to contain iron. Okay, and in this case over here, and it's a very good example. So how to solve this? Let me put my phone on the silent mode. So thank you. I'm going to start with iron, okay, because iron is going to occur in two minerals, okay, and having this into consideration is going to be a quite complicated system for me to solve, because I don't know how much of those two minerals I have together, but I know for sure that I have iron in both. Okay, so let's change our attention then to copper. Okay, if I take a look at the chemical composition of chalcopyrite, we have copper. Okay, that's the name of the mineral. Chalcopyrite means a pyrite which has copper on it. Okay, but I don't have copper on this second mineral, on this second phase. I don't have copper on pyrite. Okay, so let's take this as a reference point and let's start to distribute copper to this mineral. That will be then step one. So if you take a look again at what we have done on the first exercise, it would be pretty much the same. Okay, we have one mineral phase and we have one chemical element. So let's consider this as step one. Okay, what would be then step two? Start to divide the iron. Okay, if I know how much chalcopyrite I have and I calculate this because of the copper, then I know for sure how much iron I already used on the chalcopyrite. And I'm going to subtract this with the total iron of the total iron, and then I'm gonna distribute iron also to pyrite, and then I know how much pyrite I'm gonna have. Okay, so let's go to the molar masses and we can take a look over there how much I have of everyone. So this is the molar mass of copper, this is iron, and this is sulfur. Okay, so let's convert then copper to chalcopyrite, and I'm going to represent chalcopyrite by Cp. If I made the same calculation that I did before, oh, not quite the same, because I have now all of this. What this is mean? We're gonna take a look at this in a few seconds, okay? But let's just consider this. First of all, the concentration or the content of copper in the chalcopyrite is 22.5%. So that's why I have over here 22.5%, okay? So what is this term over here? 63.54 means the copper that I have, the molar mass of the copper in the chalcopyrite, because I have just 1 molar of copper. Then we have 1 molar of iron, and that's why we have this number over here, 55. And then we have 2 oxygens, and this right here. And I'm dividing this by 63.54 because this is the molar masses of just 1 mole of copper. Okay, so when I evaluate this, I'm gonna know that I have 65% of chalcopyrite. So now from my 100% mineral phases, I already narrow this down to 65% that I know for sure what I have. Okay, and that's chalcopyrite. So let's then move to step 2, and then we finalize with the step 3. Step 2 would be iron on chalcopyrite. Okay, so let's make the same calculation. I know that I have 65% of chalcopyrite in our ore. I can easily evaluate how much iron I have on 1 crystal of chalcopyrite or 1 mole of chalcopyrite, and I know for sure that 19.8% of iron is contained on the chalcopyrite. So we can now reduce the amount of iron that I have, which was 26.6, because I know that from this 25.6, 19.8 it's already on chalcopyrite. So what is left of iron is associated with pyrite, and that's for sure that's going to be on the pyrite. So here, how can we do this? Just calculating the iron on the pyrite, and it's going to be pretty simple. 5.8% of my iron is on the pyrite. So if I made the same calculations again, I can come back now to the amount of pyrite I have, and then we can estimate something quite nice. If I have the sulfur content, I could try to close these calculations and even evaluate my error. Okay, so if I have this, I could come back and say, okay, I estimated this amount of copper, this amount of iron on the chalcopyrite, this amount of iron on the pyrite, but the sum of this is, of course, sulfur. So if I have the sulfur content, I could try to estimate this, and then I could input in my calculations an error bar, okay, and see if I made some mistake. If not, everything would be correct. So step 4, I'm gonna try to evaluate the iron on the pyrite. Is just the answer of the first question. So straightforward, 12.5%. That's the amount of pyrite. And the non-sulfates, I can do this by subtraction. If I have 100% of my mineral phases, and I subtract the 65% that I know for sure it's chalcopyrite and 12.5% that I know for sure it's pyrite, I have 22.5% of oxides, okay, other minerals bearing also copper and iron. Okay, if I want to know how much copper and iron I have on this 22.5% phase, I just need to subtract. Okay, so it's easy for us to do this. It's not so complicated, but again, I have just 3 mineral phases. If I have more than that, the complexity would be increasing also. And sometimes I can't find that element present in just 1 mineral. And that's my main problem. And how can I solve that? I'm gonna show you guys on the next lecture, probably, how to use the Excel solver, Microsoft Excel solver. And we're going to do this to calculate circulating load on mills. And we could apply the same idea to any kind of systems like this. And I just need to write down the equations, and Excel is going to be the tricky. Okay, and pretty much I just going to click a few buttons and he's going to come out with some ideas that can solve the problem for me. So we're going to move on. We're not going to try to do this by hand, but we're going to come back later on and Excel is going to do the trick for me. Okay, so trying to summarize mineral processing in a few stages, we can think something like this. I have my run. What is run? Run of mine. Okay, so the material that's feeding my mineral process plant. I can use different names for this, but normally we like to say run of mine. So again, I'm considering that the material is going to feed directly my mineral process plant just in time. Okay, so I have this material coming and he's coming hot. Let's think like this. And I have two ideas. I have two options right now. I can feed direct my material to comminution, or I can send it to classification and then to comminution. Okay, I'm going to show you some flowcharts in the sequence right now, and I like very much that you guys analyze with me what are the stages that all flowcharts have, and what flowchart have different stages than the others. Okay, and you're going to see by yourself that comminution and classification is a sure thing. All the flow sheets are going to have this. I've never visited a mining company who doesn't have classification. I have been in many places and I never saw one single mining company who doesn't have classification. I see pretty much everything that you can imagine. Comminution, definitely you can survive without it in a few cases. Concentrations, yes, we can go by without that. Dewatering for some people is considered like a luxury accessory, but definitely we need classification. I'm going to show you guys why. Okay, but let's consider only those 4 blocks because we have 2 dewatering blocks. I'm going to group in one single block. Okay, what is comminution? It's a mineral breakage. I'm going to break mineral particles. Okay, so size reduction is going to be covered in comminution. Second one, classification. Classification for me, it's separate material according one property, and this property could be, as a matter of fact, just 2: size or specific mass. But specific mass could be also tackled into concentration. So it's a little bit confusing, but I'm going to show you that some equipments designed to classification could also be doing some sort of concentration. Okay, and I'm talking, for example, about cyclones, and they're going to do this, and I'm going to explain why and how. Okay, but just give me a few minutes. So again, comminution, quite simple, just breaking minerals. Classification, separating according size. Okay, let's think like this: size sorting. Concentration, then we're going to separate the minerals that I want to, then the minerals that I don't want to, or the minerals that I couldn't sell it. And other things that we can also think about concentration is something like this. Consider that you're going to cook something, okay? And you're going to, for example, prepare some meat. And then you have bones on your, okay? So you can use the bones for something. You can, I don't know, feed your dog, and you can prepare something with bones. But you can even prepare some other dishes with the bones, okay? I know this. But for this example, consider that you cannot use the bones. So you have to separate the meat from the bones, okay? And even some part of the meat you want to remove, like muscle tissue, or even some hard part of the meat you want to remove, okay? This stage is what we call concentration, because if we don't do this, maybe we can have some chemical elements present in our final concentrate that could be harm to our final product, okay? So our client is not gonna like it. And since in here, we cannot, and repeat, change the crystalline structure of our minerals. We're just gonna separate minerals without breaking those crystalline structure or change the chemical composition of the minerals. We some sort of have our hands tied, okay, in our backs, okay, because we can't do too much. But here's the thing: if we try to change the chemical composition of the crystalline structure, it's going to require us a lot of investment, and I'm talking about money, energy, chemicals, and the mass that we're dealing is so huge that's not going to pay off. Okay, so we have to do as much as we can in order to prepare the material to the following stages. And on those following stages, and we're going to reduce the mass, then we can do something chemically speaking. And I'm going to show you guys right now why I'm telling this and how we're going to do this. So first of all, let me introduce you to some ores, okay? And you guys are going to laugh, but I did this not by mistake, but on purpose. I wrote the word ore after coal. We don't have coal ore. That doesn't exist. That's not the definition of the word ore. Okay? I just put in here to stress to you guys how wrong this would be. Okay, so if someone from Australia is looking at this picture, they're gonna say, "Oh, I know this, mate. This is Australian." Yeah, this is Australian coal. Okay, and it's a beautiful picture. I've been in Australia once and I could see this myself, but we don't have ore. It's just coal. Okay, so what are we going to do? We have to mine this coal and we have to process this. First thing first, okay? Can I just remove the coal and left everything else right there? I can't. Okay, so I can just come here and carve the ore. Okay, I know it's not ore. Carve the coal. Okay, I have to take everything. I have to extract everything. So in order to have the coal, to recover the coal, I have to add even water to the system. And definitely, I didn't want to have water in my coal. Okay, but I don't have other technology to do this. So this is a flow sheet, very, very simple of how we deal with coal. So here comes the material. Again, run of mine. Okay, the run name it's right there. And I have a stockpile. So see, in some cases, I'm not going to feed direct the material to the mineral process plant. I'm going to have some stockpiles. And why I'm going to have some stockpiles? First and most important, homogenization. Okay, if my material is too heterogeneous, I'm going to have to pay for it. And I'm going to pay in order to promote a stockpile. I'm going to show you guys some stockpile pictures from Catalan. They are very nice. I like those. And to be 100% honest with you guys, it was the first time in my life, my professional life, that I came to a mine and saw a huge stockpile. Because every time that you drop minerals on the floor, you're breaking the minerals and you're spending money. So making stockpiles, it is, on the first vision, on the first approach, a waste of money. Okay, but then again, if you don't do this, you cannot blend your minerals in order to have an homogeneous feed to your mineral processing plant. So you have to do it. Okay, it's better for you to spend money on this stage than to pay the price feeding your mineral processing plant with garbage. Okay, why? Because we do love to work with steady state conditions in our mineral processing plant. So consider this: if you're preparing juice, okay, so you're in the kitchen and you're going to prepare juice and you're going to use the blender. Okay, if you're going to produce just like this, carrots plus orange juice, you're just going to put together and you're going to blend this. Okay, and you're good to go. So you take the orange juice, you take the carrots, you put together, you put sugar and you blend and keep going. Okay, and if you have to repeat this for the whole day, that's not a problem because you're only going to work with orange juice, carrots, and sugar. Okay, but just now consider this: every order that arrives to you is from a different juice. So you have now pineapple, watermelon, anything that you can imagine. Okay, apple juice. In order to avoid contamination, you have to stop everything that you're doing. You have to clean everything and then move to the another fruit because you're going to do a different juice, and you're going to lost a lot of time by doing this. Okay. Eventually, you're going to hire someone to stay by your side, and you're going to have more than one equipment just in order to change faster, in order to increase your productivity. We can't do this in a mineral processing plant. Okay, we can't. It's not going to be feasible. So what we do is we can have many drill machines, many drillers, many loaders, many trucks, and they can be working in different spots in our mine. They can bring everything together to the same spot, to the same place. Okay, I can even crash everything or crush everything together that's not a problem. But then I need to have at least some idea of what is going to feed my mineral processing plant or the rest of it. So I need to have this idea of how much material I'm going to need, how much material I'm going to receive, and what are the grades of the material. And that's why stockpile is the best option. Okay, so I'm going to track, literally, I'm going to track how much material is coming to me from these different points, from different positions in my mind, what are the chemical and geological composition of every single point, and how much mass I'm adding to the stockpile of this material. Then I'm going to do this in a way that by piling up the material and reclaiming the material, I'm feeding my plant in an homogeneous way. Okay? And then definitely I can work with that. Okay, so as you can see, we have screening. It's right here. I'm going to make the size classification over here because I'm going to have a cyclone separator. This is concentration, people. Okay, and then I have a cyclone sizer. So if I'm doing concentration right now, I'm separating the material that I want and the material that I don't want, and that's why I have this plant refuse. See, they're not calling this tailings. They're quite clever. Refuse, and this go to a rock dump. Remember the waste dump, the waste heap that I mentioned to you, that's the material, okay? And in here, I have water recovery. What is water recovery? Dewatering. So one stage would be classification, it's right here, stage 1. Second stage, concentration, it's right here. Third stage, right here, dewatering. What we didn't have yet was concentration, okay? No, concentration we have, it's right here. What we didn't have was comminution. So why we don't have comminution? Because in here we have another concentration, okay? So it's here, in this reflux classifier, it's going to make for us what? Classification again. Okay, what we don't have in here is comminution because we don't want to break our code. Okay, so in this flow sheet we can go by without comminution. Yes, yes, that's okay. We already have fine particles. But how about gold ore? And now it's ore. Okay, now we can say this with our mouths really full. It's ore. And in this picture you can see a different kind of ore. Okay, not all gold is processed like this. Okay, this picture shows us free gold. Okay, so we're talking about gold nuggets. This is one kind of nugget. Sorry, this is one kind of gold. Normally, it's not every single deposit that we have nuggets. On the other hand, we can have gold inside of the sulfide minerals crystalline structure, and then we need a completely different setup in order to recover this gold. And I'm going to show you guys this. Okay, but this gold, it's quite attached to what? To quartz. Okay, so take a look at this. The gold is attached to quartz. How can I remove the gold from the quartz? There's no other way. I have just two options. Just two options. One, I can chemically dissolve the gold. I can do that. Okay, then again, it's not going to be mineral process, it's going to be hydrometallurgy, but I can do that. On the other hand, I can try to break everything down, okay? And that's what I'm going to do. So let's take a look about this flow chart, and it's coming from Lundin Gold Mine, okay? And what they do is crusher. Oh, here we have comminution. Then they pile up, they crush again, and then we can do this gravity concentration over here. We can do this flotation over here. So rougher, it's one of the flotation stages. We have actually 3: hoffer, cleaner, and scavenger. And we're gonna come back to this in the future. Okay, so here we have rougher, here we have scavenger, and probably we're gonna find some clear somewhere around. And if we don't have any clear around here, it's because they narrow down this flow sheet. Okay. But then we have regrinding cyclone. Oh, what are they doing right here? They're doing two things at once, okay? They don't want to show you this, but they have a mill over here somewhere, and they have cyclones closing the milling loop. I'm gonna show you guys what this means, okay? Then they have flotation again in here, so probably the cleaner could be something in here. From this part on, then we don't have mineral process anymore. Okay, so this is the barrier, this is the fringe, of mineral processing. So here we have MP, and here we have hydrometallurgy. Okay, so nothing like Hail Hydra, but this is Hydra, hydrometallurgy. And here we have concentrate, and then we have concentrate stockpile. And if that's the case, I'm going to just ship this concentrate out. Okay, if not the case, I can go to a circuit like this. This is carbon in leach circuit. It's also used carbon in pulp circuit, but I'm use activated carbon in order to remove the gold from the crystalline structure, or even golden nuggets. That's not a problem at all. I'm just going to add some chemicals, some cyanate, and I'm going to dilute, dissolve the gold, and then move the gold from the mineral phase into the carbon phase. And I'm going just to reclaim this gold later on by electron winding. And then I have this doré production, and then I have this doré, and doré, it's gold bars. Okay, and I'm just ready to ship it. So if you take a look at this flow sheet, or this flow sheet coming from True Gold, you have pretty much the same that I mentioned to you. It's just a little simplified overview. What they are showing to you is I come from the mine, I pass on the classification stage, go to crushing and milling, then I have stockpile, and then I'm going to metallurgy. Of course, they took out every part of concentration in here. They didn't want just to mention this, but in the end, you have the golden bars, okay, the golden doré bars, okay. So how about copper? And here again, or the copper in here is the bluish material. Okay, so this beautiful bluish material, that's the copper ore. And again, it's really attached to the other minerals. How can I separate those if not breaking? There's no other way. Okay, so let's take a look at this. It's a little bit more complicated, right? Yes, it is, but it's nothing that we can't do it. We can do it. Okay, so what I intend to in my next hours with you guys, not only today, is to show you every single item on this image that belongs to mineral processing. Okay, so you're going to be able to take a look at this and say, oh, this is a jaw crusher. This is what? This is a cone crusher. Okay, because it's secondary, because there is have a spider on top of it. It's a cone crusher. Okay, this is a vibratory screen. This is again another mill. Okay, but it's different from this mill over here. Yes, because this could be a bar mill or a ball mill, but this is a sag mill. Or what is the difference between a sag mill and a bar mill and a ball mill? We're gonna see this. Oh, this is a thickener. Okay, oh, this is a press filter. What we have in here and how these things, this machine work. That's what I'm going to introduce you. But then again, we have the same things. Take a look at this. Crushing. Oh, I know crushing. Okay. Oh, this is leaching process. This is not mineral process anymore. Yes, you're right. So from this part on, we can say that's not mineral processing, but we have crushing in here. Okay. If you go to the other part, you're gonna see crushing again. Okay. And they put this grinding over here. They put this Krebs. Why this name Krebs is popping up? Because Krebs was a former company who manufactured hydrocyclones, and F.L. Smith acquired Krebs. So this flow chart is quite nice, but they're only showing the equipment that they used to sell. Okay, and that's why flotation is right here, dewatering is here, and also in here. Okay, so yeah, we can see all of the blocks over there. And what is this? This is PGM ore. Do you remember our last lecture about strategic minerals? So you take a look at this, and you can imagine that these guys in here, take a look, these guys in here, they are carrying PGM. And you're probably going to think to yourself, Professor, but that's nothing. That's literally nothing. What is this? How much I have of this material? If we talk about gold, normally in Brazil, it is considered a gold mine if you have a grade of gold around 1 gram per ton. So 1 gram of gold per 1 ton of mineral, or rocks. Okay, so I have to go to my mine and bring back 1 ton of material, okay, of ore, and feed my mineral process plant to produce, in the end of the day, 1 gram of material. That's the amount. And if you consider that if you go to your kitchen, if you want to prepare something, you're gonna add, for example, to bread, you're gonna put something like 3% of salt in your bread, up to 3%. Okay, so if you're preparing meat, 3% is quite good. If you're reducing on salt, you're gonna be ending up like 1%. I have to remind you guys that 1% is 10,000 ppm, and 1 ppm is 1 gram per ton. Okay, so consider this then. Okay, that's the amount of material that we're dealing with and the grades that we have to deal with. So it's quite normal for us, even on papers, to see the flow chart represented like this. So get used to have this. Okay, it's quite normal. And this flow sheet, for example, I took from this paper that you can see on the upper part of my slide. So I got this ore rich in in PMG materials, and here I don't agree. I disagree with the author because he used the PMG letters, and I prefer platinum group minerals. Okay, but let's put this aside a little bit. So I have what? Concentration, crushing, milling, flotation. And then we have what? Smelting, and so on and so on. So we have metallurgy. After this stage over here is just metallurgy. Okay, in this case, pyrometallurgy. So we have fire, we have heat. But this author, he put in here the mineral process being composed only by crushing and milling. And why he did this? Sorry, because for many stages of processing, we just consider the classification. It's something that you have to do. Okay, it goes without saying. You can't do flotation without classification. Okay, it's like impossible. And then you just don't need to mention. Just go straight to crushing, milling, flotation, and everybody's going to know for sure that you have other things around it. But how about gems? And I included this just because someone asked me about gems last lecture. Okay, so I come back and said, okay, I have to put gems. How about diamonds? Should we crush diamonds? Should we mill diamonds? Because it's quite strange, right? If you consider that the price of the diamond increased a lot with the diamond size, you probably don't want to break your diamonds. But nevertheless, you gotta do it. Okay, as you can see over here, and this is from Botswana, and I just feed the material in here. This is only a grade to remove the larger size of the material that I don't want to feed my jaw crusher. But right here, then I have again classification, grinding, stockpile, then mill. I'm gonna mill diamond. See, it's incredible. But yeah, we do this. We have grinding again. We have classification over here, grinding in here, dewatering in here, okay, dewatering in here. We have concentration in here by dense media concentration, then magnetic separation over here. So we have concentration, and we have over here again a screening plant, and this screening is going to do what? Using XRF, they're going to try to do some sorting. So they're going to take a look at the material and say, oh, this is diamond, take it back. Okay, so I'm doing some ore sorting. Okay, we can do this manually, but definitely if we use XRF, X-rays, we can do this better. And those are the called rejects. So in here, probably the author not very connected with the mineral area because we don't call this reject. Actually, when we translate the tailings word to Portuguese, it's going to be reject. Okay? But the word in English is tailings, it's not reject. And then we have over here hand sorted diamonds. So yes, guys, we need to break and to classify and concentrate and dewater everything, including diamonds. Okay. So what kind of classifiers do we use? And in here I could start by showing you guys, for example, the comminution and then followed by classification, or I could start with classification and then move to comminution, and I decide to do this. Okay, so we can have air classifier or water classifier, and it's so important to us that I put screening outside of the classification. Okay, but the idea would be air or water classification. So if you're using a screen and you're not adding water to it, it would be like an air classification. Okay, if you add water, then it would be wet classification or something like that. So I put just two examples of each. So I have a regular vibratory screen in yellow. It's this guy over here. So this is a vibratory screen. This is a high frequency screen. I think I didn't add anything of high frequency screen yet for you, because I'm gonna come back to this when I'm talking about dewatering. Okay, over dewatering, we're gonna talk about high frequency screens. So this in here is an air cyclone, and again here we have some names problem, and I'm gonna come back to this when I'm talking about hydrocyclone, and this guy is called cyclone or hydrocyclone. This is a spiral classificator, and this is an air classifier. Okay, there is many options to air classifiers. This is just one of those. It belongs to Metsu, and in the future I'm gonna come back also to this. I'm gonna show you guys a zigzag classifier working. But first of all, what is the difference between screening and sieving? And I have reviewed dozens of papers. Okay, I have wrote a few of those, but I have reviewed dozens of papers, and sometimes I just receive this confusion. Okay, the author are actually writing down screening and he means sieving, or in the other case the opposite, but it's always the same. He wants to say one thing, but he actually write the other thing. Okay, so guys, do you know what is the difference between screening and sieving? I'm gonna tell you today, and probably you're never going to forget. Okay, so just keep that in mind. It is a batch test or is a continuous flow? Just ask yourself this: it's a batch or it's continuous? If it is continuous, it's a screening. If it's a batch, it's sieving. So on the right hand side, we've seen sieving. Okay, so that's the sieve that we use to make this granulometric analysis in our lab. That's one of the machines. We have at least 3 types. This is the roll tap. Okay, and on the right hand side, what you're seeing is a screening, an industrial screening. So please, people, if you perform in your test something in the lab and it was a batch separation, a batch classification, you did sieving. Okay, you didn't do anything like screening. You didn't do this. Okay, so since we're talking about sieving and screening, we have to talk a little bit about particle size distribution. Okay, because the materials not come to us with just one size. Okay, the materials come to us with many different sizes. And I know that the material is actually discontinuous. It's not a continuous function of the sizes, but nevertheless, it is a continuous amount of material. So we can use sieves like that, or even screening panels, and the aperture could be circular one, or I can use a rectangular one, or even a square one. That doesn't matter for me right now, but nevertheless, one concept that is quite important is the mesh content. Okay, the concept of mesh is something like this: I'm gonna measure 1 linear inch in my sieve or my screening panel. Okay, just 1 inch, and I'm going to count how many apertures I have in this 1 inch. So take a look at this example. The other pictures come all from the Wheels and Finch book, but this one I added some extra items. So from this part to this part, I have 1 inch. Okay, just 1 inch. And how many apertures I have? I have 1, 2, and 3. Okay, so this would be automatically say 3 mesh. Okay, so this sieve would be a 3 mesh sieve. If I take a look at this one over here, this is a number 10. Okay, so what that means, number 10, if I take a look over here, I'm gonna see 2 millimeters aperture. Okay, so this over here is 2 by 2 millimeters. And if I take a look over here, I'm gonna see extra numbers, but the number mesh come from here, okay? And in Brazil, you're gonna take a look at your sieving and you're gonna see a label like this. And on this label, you're gonna see three numbers, here, in here, and in here. This first one would be mesh. This other one would be also mesh, but this one would be a Tyler mesh. And what is Tyler? It's this series coming from here, Tyler. It's this USA company. So you have this number automatically wrote in here. And in here, we have a different mesh number come from A, B, and T. Brazilian Association of Technical Standards. Okay, so it's a little bit different, and that's why you have to know the difference. And I'm gonna show you one table, but if you don't know, you just take a look and you write down. And over here, you're gonna see the aperture, this size over here of your screen in millimeters or micrometers. Okay, you just write down. If you're in the United States, this number would automatically means to you 10 mesh. Okay, so let's move on. Here we have on table 2, let me start with my right hand side, the aperture. So if you have a screen number 3 or 3 mesh, what you're gonna have? 5,600 micrometers or 5.6 millimeters. Do you remember the 10 mesh? Here it is, 10 mesh, and you're gonna have something like 1.7 thousand micrometers. Okay, 8 mesh is actually 2 micrometers. Wow, but you just showed us one sieve, and that sieve was number 10, 2 millimeters. What is the difference? Sometimes you can end up having a small difference between one manufacturer to the other. That's why it's paramount importance that you go there, you take the sieve and you write down the exactly aperture of the sieve, and not just go to a tab and a table and take a look at that and said, okay, I'm gonna use this number. You can make some mistakes. Okay, you can make really mistakes. And on the table 4.1, I'm gonna try to show you guys something quite important, different equipments. All of those equipments can do the same thing, give you the particle size distribution. But some of these equipments are better suited for some sort of material. For example, I can do a sieving, okay? Definitely, I can do both sieving, like dry or wet sieving. But do I am gonna get my material fractioned after the test? Yes, definitely I'm gonna have this. So if I go there and put like 9 sieves, after the test I have material fractioned in 9 parts. And I can perform the chemical analysis of these 9 parts of my material. And that's what I call it, chemical and granulometrical analysis, and I call this granulochemical analysis. Okay, so what is a granulochemical analysis again? I take the material, I go to the sieving, and I'm going to separate the material according to the size, and then I'm going to analyze chemically the material according to the size. And that's one of the most important tests that we perform daily based in my lab here in Brazil. But what is the size that I can actually work with this material in a sieve? Here the Wills is proposing 5 micrometers, and I disagree. Okay, I strongly disagree. I can go up to 25 micrometers. Okay, it requires more work from my side, but I can do it. It's doable. I have to add dispersant material, and normally I use a chemical called sodium metasilicate, and I put like 5 milliliters, 1% of sodium metasilicate on our material. I add water, and then I perform the sieving, and that will be in a sieve of 25 micrometers, or you can call this 500 mesh. Okay, it's the same. But below that, like 660, it's on the market even to 800 mesh. Okay, but it's impossible to have a real good sieving in this kind of sieves unless you add more equipment. For example, ultrasound. If you start to perform using water pressure, but for the daily base and for the control products that you actually produce in your processing plant, that doesn't work. Okay, I completely suggest you guys to move away from that. So if you have this very fine particle, what you should be doing is or laser diffraction, okay, electron microscopy, and you can do even particle size analyze using cameras, CCD cameras, like optical analyze, and it works. Okay, it works quite nice, but move away from sieving. Okay, you can have other options like elutriation using cyclosizers. You can even do this by gravity separation, but it's pointless because normally you don't have an equipment in your industry who can actually do it. So in the lab it's okay, you can separate the material, but what are you going to do this? At the end of the day, it's going to be thrown out on the tailing dams. Okay, so keep on the upper part of this table and you're going to be safe. Okay, so after I do the sieving, what I'm going to get from that, besides of having my material stratified according the sieve that I use on the test, I'm going to have this curve, and this curve shows to me my particle size distribution. This is not coming actually from the sieving. It's beautiful like this because I use halos from Sympathec, which is a laser diffraction equipment to perform my analysis, and this is quite beautiful. Okay, it's what you expect to see in a particle size distribution, and this is a real deal. Okay, so this is a material that we actually had on our hands in Germany when we were working with this material. But I'm going to show you some more complicated cases. Okay, so taking a look at this graph, it's okay for most of the people, especially here in Brazil. People are going to look at this and say, oh, this is okay, because I can say the size of the material that 90% are below it. Okay, so I have 90% of the material smaller than what? 200, it's going to be like here, 200 micrometers. I can say for you on the other hand side, how much material I have below, for example, 20, it's right here, 20 micrometers, because this material, I'm going to remove this, I'm going to call this material slime. Okay, I don't want to tackle with this, it's too fine. And how much material I'm going to lose to the slime fraction? Oh, less than 10%. Okay, I can work with that. And why I'm telling you guys those numbers, because from 20 up to 200, it's normally the threshold for flotation for our main concentration. Okay, so just looking at this, I can have a glimpse on what I'm gonna have in our hand. But that's quite tricky, because let's consider this example over here. Okay, I have 4 different materials. Actually, it's the same material but in different size. Okay, so I have these 4 spheres made of alumina. If I weigh this material, I have 109 grams per sample. Okay, so if I come to you and ask you, how much material I have in every fraction, you're gonna tell me the same. You have the same amount of material. You have 190 grams on A, B, C, and D, and he is right. Okay, but another student can come to us and said, oh, he's wrong. You have 573 spheres. Okay, you don't have 190 grams. You have 573 spheres, and actually you have one sphere, just one sphere, on the size of 4 centimeters. So it's a completely different approach, because when Ramon come to us and said you have the same amount of material, 190 grams, you can instantly imagine that the 4 parts are exactly the same, and they're not. Okay, so one thing is the mass, and one thing is the particle number. Okay, guys, so one thing, mass, how much mass I have in every fraction. The other thing is, on that size, how much particles I have in every single one. Of course, I can use math to translate one to another. Okay, if I know that I have only spheres, and if I know the specific mass, I can just calculate one to another. But that's not so simple when we're talking about ore. Okay, but let's move forward a little bit. So what we have done here is, I went to the lab, took the material, performed the sieving, and then I have the red curve. Okay, is the result. But then I take a look at this table on the top, and all this material is coming from Microtech. Okay, Microtech has something very nice over there for us in order to study sieving. So what they done was they performed that spheres test that I mentioned to you before. So as you can see over here, I have 4 different sizes. I have 5 millimeter spheres, 10, 15, and 40. and all of those 190 grams. So if I calculate the percentage of material in those fractions, I have 25%. The sum is 100%. So I can come here and plot this graph. Okay, that's the particle size in micrometers according to the amount of material. So every time that you see 3, the number 3, it means accumulated, percentage accumulated. Okay, but percentage of what? In this case, mass. Okay, so we have one thing over here, mass. But I can go to number. Okay, Santiago, for example, he came to us and said, oh, no, I counted. Okay, I have 1 sphere, 18, 64, and 490 spheres. And if now I try to make this percentage, an accumulated percentage is going to be completely different. Because take a look, now I have 0. 0, it's not accumulated. Okay, 0 is just the percentage. So 1 sphere in 573 accounts for 0.2%. 18 spheres account for 3.1 spheres of the total. So take a look at this, guys, and it's quite interesting. The majority of my spheres are on 5 millimeters size. Of course, has to be. I have 85.5% of all spheres on that size. Okay, and I have to deal with this material. I'm not dealing only with masses. I'm dealing also with number of elements, and that's why we're gonna have these bars over here. Okay, so these bars, as you can see, the auto put this only for the sieves. Now we're gonna take the bars down. We're gonna move all of the bars down, and we're gonna have what? A histogram. Okay, so what is the histogram that we're gonna see in this chart? Is the amount of particles that we have on this particle fraction or this particle size. So in this over here, we can see the same example, but we just move the bars down, and now we have two informations in the same graph, and that's the way to do it. Okay, please guys, that's the way to do it, because we have more information now. So on one x, on one vertical x, I can see what? Q3. Okay, on the other one I can see what? P3. Q3 for me, it's what? Mass. Okay, and P3 on the other hand for me, it's what? Number of particles. And what you can see over here, definitely you have material on the coarse part, which is on your right hand side of the graphic, and you have fine particles. But the majority of my particles, of my mineral particles, are around which size? This one over here. That's the majority. Okay, so you have a small amount of material on one end and in the other end. And you can tell me, oh, but this is quite easy to see in here, and it's easy to see in here. Okay, it's easy to see on the outer parts, but it's not easy to see in the middle. Okay, it is impossible to see in situations more complicated. Okay, so here is the result coming from Hilos. Again, I took that beautiful material that I showed to you before. That was a calcite sample that we prepared in our lab in Brazil and took with us to Germany. Okay, so it's the same graph. Okay, it's the same graph that I showed you right in the beginning. I'm showing again, but this was plotted by Hilos software, and he's giving to me right here Q3 in one hand, and in the other hand Q3 again. Oh, but it is capital and it's lower. So one is regarding mass and the other one is regarding number of particles. Okay, and then I have this histogram in the middle. So in here you can analyze and say, oh, no big deal. I can see very nicely both distributions. Okay, so let's consider this. I have now not one material, not one mineral, but I have two minerals. One mineral, it's quite difficult to break, and the other mineral, it's quite easy to break. And I'm going to break both together. Okay, the same machine. I'm going to just feed the material and break the material. After the breakage, I'm going to have two populations because I have two minerals. One population is going to be coarser than the other because one population is difficult to break, it's more resistant. So I'm going to have one curve that's actually a misinterpretation of two other curves. And that's what I'm telling you in here. So take a look at the particle size distribution. You're going to have something like this. Yes, over here. What information you can draw from here? None. You're going to take a look and say, oh, okay, this is my material. But actually, I have this coarser material in here, this fine material in here, and you're seeing the two, literally, you're seeing the two waves together. So I can't have any information, good information, reliable information from that, because it's missing one. It's missing what? The histogram. So now let's take a look at this more complicated situation, okay? So if you take a look at the particle size distribution, the S curve is this one. And there is something strange in here. When I saw that, I said, there's something strange over there. So let's take a look at the histogram. And then you have this peak over here, and you have this peak over here. What do you conclude about this? You have two particles size distribution, okay? In this case, I have only apatite, pure apatite that I prepared in my lab and took with me to Germany. But what I can see in here was when I performed the sieving, because this material was sieved, actually I had two different populations together, okay? And that's why in here, I almost don't have anything. So this is material prepared in one sieve, and this is material prepared on the second sieve. And when I mix together, I have these two populations, okay? And right now, I have a PhD applicant in Germany, and I'm her co-supervisor, and she was dealing with flotation of tailings. Thus, only by this, it's complex, okay? But she's actually floating tailings from Corvo Neves. It's a mine from Portugal, and it's a gold mine, okay? So she was trying to perform her test in the beginning, and then I came to her and said, Anna, do you have the particle size distribution? She said, I do have it. It's very fine particles. Okay, let me take a look. And we saw something like this. And we decided to did what? To make a sieving of the material, regular sieving. Because if I went to hydrocyclone, I had other problems, and I'm going to mention in the future. And then she could cut this distribution in two. And she's now performing coarse flotation and fine flotation. And it's working. Okay, she now can recover these minerals, the sulfides, by doing this. Okay, just taking a look at the materials and thinking, what do I have in hands? Okay, so it's quite important to have this. And if your material is complex, just like what we have in here in Catalan, then prepare to see things amazingly surprising, like I just showed you guys. So let's go to industry. Okay, if you don't have any questions, if you have a question, please let me know. Okay, just raise your hand or open your mic. Oh, Ramon, feel free, go ahead, ask your questions. Sorry, Ramon, I can't hear you. You're muted. Yes?
Sorry. Okay, you talk about two different materials after sieving. And you use one set of sieves of it's different of after sieving. You analyze the type of material.
That's correct. Yes, that's correct. Sometimes, Ramon, your material behaves differently inside of the mill. Okay. So, for example, here in Catalan, when we talk about phosphate rock, we have associated with it iron ore minerals, iron-bearing minerals. I think it would be better consideration because we have not only hematite, not only magnetite, but we have also goethite. Okay, and goethite is not considered nowadays iron ore mineral, but let's consider just that iron-bearing minerals, and we have to remove this iron. And one way to do this is magnetic separation. Okay, so when you go to the mill and you take a look at the material, the iron-bearing minerals, they are way more difficult to break than the phosphate rock. So we do something like this. We break the material, go to the magnetic separation, and we move the coarse fraction. Okay, the magnetic separation of this coarse material, we just remove those. And if you ask me how much phosphate rock you're losing in this stage, because you're losing phosphate rock, definitely, we have something around 25 up to 35% of our ore composed by iron bearing minerals. So it's a lot, okay? It's a lot. But we can't use these iron bearing minerals because the phosphate content is too high to use this on pyrometallurgy to produce steel, for example. So when we remove this, the amount of phosphate rock that we lose, it's below 5%. So it pays off to remove this material inside of the milling cycle, then to have a continuing milling, liberate the apatite and the phosphate rock, for then after that perform the separation, the concentration. So it doesn't pay off. It's better just to get rid of that and to lose a little bit of phosphate rock than to keep insisting on grinding the material and process later on. Okay, so it's quite regular to have this. Okay, I have been working with minerals that sometimes it's easier for us just to remove the coarse part, the coarse fraction, because the material that you want is not on the coarse, it's on the fine. That's the niobium case, for example. The gold case, you just go for the fines. You don't have anything on the coarse fraction. But it's strange, but sometimes it's the opposite. The coarse fractions is what you want, okay? And then you just throw away the fines and keep just the coarse particles, and then you go to a mill with this coarse fraction, and then you keep grinding, and then eventually you go to concentration. But yes, you can have like a pre-concentration of your material by doing a screening, okay? By using classification to do this, and works pretty good.
Okay, thanks.
I'm not sure if I answer your question, but if that's the question, yes, you can use this information in order to enhance your capability to process your material.
I understand. I understand.
Okay.
Yeah.
Any other questions?
For now, not.
So thank you for stopping me. It allows me to drink coffee. Okay, so yeah, it's quite good.
Okay.
So let's go to see some screening equipments or classification equipments working. So this picture was taken here in Catalão, in the phosphate company that we work close to. This coming from Copebras. It's an old picture. It's from 2015, but the equipments stay in the same place over there, in the same functionality. So you can see over here that we have a vibratory screen over here, okay? So taking a look at different angles and different places, that's the screen. What it's going to do is pretty straightforward. It's going to vibrate, and by vibrating, the material can pass through these apertures over here. And I want to draw your attention to this panel itself, because you can see that the aperture of the panel in here is different than in here. So this is quite common because we are dealing with a banana screen, and the banana screen has this name because it's round. So when you start at the beginning of the banana screen, you have one inclination, and when you go moving into the end of the banana screen, the inclination is going to change, so you change the aperture of your screening panel, okay? So in the end, you have the same aperture, but you have different positions. How we do this? Let's consider this cell phone, for example, okay? If I show you the cell phone like this, you're gonna see this as the aperture of the cell phone. But if I do this, if I incline my cell phone, you're gonna see a different aperture for the same phone, okay? So at the beginning, we have a high inclination, and that's why we try to do this with the cell phone, okay? Then I move on, and I'm gonna do this with my aperture. So, not with the aperture, sorry, I'm gonna do this with the panel. The panel is changing. So I change the size of the aperture in here to balance the inclination of the panel. So the projected aperture, it's always the same, okay? As you can see over here, we have 3 screenings altogether. I think this picture clarifies a little bit about the vibration. And in here, we're using panels made of polyurethane or just PU. But we can use rubber, we can use steel. There are other options. The polyurethane is quite nice because it's strong, it's quite reliable, it's resistant, it's tough material, it's an engineering material. And actually it can bend, okay? So if you have a material that is clogging your apertures, your screening, by this movement and by this deformation, this bending of the panel, it's going to be released, and then you don't have this problem anymore. So it's quite good. I brought you guys some video from Matsu. It's also available on YouTube. I'm gonna let the link below so you can take a look. But we can see these things coming together. So we already saw a lot of trucks moving around and things like that. Okay, so the focus is not on the Caterpillar truck anymore, but now we have a stockpile. Okay, so let's pile up our material and then we transfer this material to grinding stations. That's grinding, because this is a system that we're gonna have an in-pit grinding. Pit is the mine, okay? It's the open pit mine, so we just say pit. And we're doing this first breakage inside of my mine, okay? And then we have sieving inside of the mine too, okay? Or close connected to the mine. And this is working quite nice in many places around the world, especially in Europe, okay? And this video is quite nice because they're going to show you guys some different elements, starting with the screening. So here you can see 3 decks screening. So the first deck is the upper deck. We tackle with the coarse particle, then the middle ones, you call this middlings, and then the fine particles. And the motion is elliptical. It has to be elliptical. And the center of gravity in every good screening has to be in the middle of it. Okay, so it has the system called self-synchronization, that if the 2 weights come off, they just synchronize itself. Okay, and then you have the maximum of the screening that you can have. You can have an inclination of 5%, which is not a huge inclination because it's not a linear, but it's more like a circular sieving. But if you consider linear sieving, and I'm going to show you guys a linear sieving in the future, you can reach up to 38% of inclination, okay? And then it's showing you guys that it's possible also to have variations into a circular movement, okay? Just by changing a little bit the gravity center, okay? Let's just take a look at the simulation. Well, by doing this, by changing the stroke and configuration, your screening, you can reach higher angles. Okay, if you increase the angle, what's going to happen is you reduce the time that your material is going to be held inside of the equipment, and then you have more throughput, you produce more material. Okay, the video is going to continue on, but it's going to show you some mechanical parts of the equipment. And to tell you the truth, we're not so eager to see lubrication circuits and things like that, but you can see all of this in the YouTube later on. Okay, so this is a linear sieving. Okay, it's quite different from the other one, but as you can see, everything is encapsulated. You don't have powders around of you. So this one is used, for example, when you're producing cement. Okay, so you're producing Portland cement, and in the end of the process, you need to screen the material in order to allow you to return the clinker back to the oven, or even grind the material, grind the cement if you need so. Okay, so you can use this kind of sieve. As you can see, the motor or the vibration system is below it, it's not on the top of it, and as I mentioned, it's all closed. You can see many leads over here, and then you have 3 products because you have 2 decks. That's the first deck and that's the second deck. Then you have 3 products. Okay, the last kind of screen that I want to show you guys, because it's quite important for our discussions here in Brazil, is the trommel. Okay, so some people call it trommel screens or just trommel, and I want to show you this footage from Australia, and that's the main application of trommels nowadays, and quite important application for us here in Brazil. So this guy over here, he's just using the bobcat to transport his material. Take a look at the coarse material. He doesn't want coarse material. So this is the feeder. Below it, you have a transport belt. Okay? So the feeder feeds the transport belt. The material is going up. And as you can see, the particle size distribution is really large. You have many different sides of material. And we go straight to the trommel. Okay, the trommel is going to be a drum, and it's going to be a rotary drum, and you have to add water, a lot of water. And by rotating this trommel, you sieve the material. So instead of having vibration, what do we have is rotation. Okay, and he is going to explain to you why he came with this design, why to put this cone in the end of the trommel. He has many explanations. It's quite nice. But this is part of the Golden Rush. If you guys want to have something to watch over the weekend, go to Golden Rush. Okay, Golden Rush, it's really, really good because it's like our, and by our I mean miners, uh, showcase. Okay, if you take a look at that kind of actually real deal, how things are being processed, you're gonna take a glimpse of how we deal with things in mining. And here he has a pen, and he just used that gravitic pen, and he can show you right there that we have gold in our hands. Okay, so this is artisanal mining, but it works quite good. Okay, so we do a lot of this in Brazil. And here we have Mecca, it's another manufacturer, and he's gonna show us how things work out for them with these screenings. Okay, so I left this for the end just for you to take a look on the difference between those equipments. And people, don't get me wrong, but there are infinite kind of designs and equipments, and everyone is going to come to you and say, oh, mine is better. Okay, because it's not a banana screen. You can see that it's completely flat, and we have this and that models and this different designs and upgrades, and my equipment is going to be better. Okay, but I only left you to see this because they do have a very good screens, and they do this very efficiently because they're going to mix rubber, polyurethane, and also steel in the same equipment. Okay, and by doing this, these three things getting together, they can enhance productivity. Okay, it's quite good. And also all the modular stuff that they put together in their screening make this really a very good engineering art. Okay, one thing that I don't like in their equipment is this shaft over there, this axis over there, because your material actually goes together with it. So you're working and you can listen to material come together with the axis, the hitting the axis. Okay, I don't like this very much personally, but actually it does do the trick. Okay, it works. So we have to tackle with that. Okay, so in a few seconds we can see right now the screening working. Okay, it's a mechanism completely different than what I showed you from Metsu, and now we can see it on real application. Okay, they're going to show us one application. As you can see over here, the way that the material vibrates on top of the screen is completely different. Metsu, they were eager to show us that the material was going to perform an ellipsis or a round movement. And in here, they don't want to show you this. It's a linear movement. Okay, you can see that the material is just jumping, and exit the screening. Okay, and here's the machine working, and it's quite interesting because it definitely do the trick. It does the trick. Okay, so let's move on. That's the spiral classifiers. Now we're talking about water. You have to add water. So slurry go inside of this material and it starts to sink. So the coarse fraction goes down. It sinks in the equipment, and this spiral just transport the material up. Okay, the fine particles, they're going to be dragged with the water and they're going to exit the material. That's the overflow of the equipment on this part. So the underflow exits the machine in here and the overflow in here. So here overflow and underflow. Okay, so I'm going to show you just some pictures of this equipment working, and this is also called screw washers because people who deal with sand, they need to wash the sand, and they use this equipment because it works quite nicely. You just remove the fine particles of the sand just by washing your sand. Okay, so in here you can see that we need water. That's why we have a lot of water around us, and in here we can add some extra water in your equipment on the top, but in here the coarse fractions go straight to this part and the fine particles goes on this tube out of here. Okay, and we have again many designs, even something strange and crazy like this. This is a well washer. Okay, so you put your material inside with water, the part is going to sink, and this well just collect the material and transport your material out of the equipment. Okay? So yes, guys, if you have an idea and you think it's a brilliant idea, go for it. Produce your equipment and send me some videos, and I'm gonna show to my future students that you propose some different machines. Okay, I will be glad to show your equipment. Guys, to almost finish up our lecture today, I have to go to hydrocyclone. Okay, and in here we can have air cyclones and we can have water cyclones, and then we have these three different names. We have air cyclones, water cyclones, or call it hydrocyclones, and people who just say cyclone. Okay, let's consider something first. What does this machine do? One thing that you can say for sure is it's going to separate material according to size. Okay, I can see over here that we're feeding yellow spheres to our equipment, and also we're feeding something like gray or greenish material and blue material, and they are separated. No, actually you're not seeing this. Okay, so what you're seeing is blue is the yellow particle trajectory inside of the hydrocycle. Okay, and what are you seeing in green is the water trajectory inside of the hydrocycle. Okay, so almost all the water are going up. Okay, because up is where the fine particles goes out. Up is my overflow. Okay, so the overflow is going up. In here we have my underflow. And that's the place where the coarse particle leaves the hydrocycle. Okay, so let's consider this first example. I have the same material, same alumina spheres that we have before in our hands, and I'm going to feed the hydrocycle. I want to do this under pressure. The slurry that enters the hydrocyclone has to be pressurized because the hydrocyclone itself doesn't have any moving parts. Okay, so everything has to work inside of it without extra energy. So when I feed this, I'm going to do this tangentially to the hydrocyclone, which means I'm going to do this close to the hydrocyclone wall, and the material is going to start to spiraling. And by spiraling inside of the hydrocyclone, what I'm going to produce is, in the center of the hydrocyclone, a low pressure area. In this low pressure area, the fine particles goes through it and leave the hydrocyclone. On the outer side, on the outer part of the hydrocyclone, I produce a high pressure area or zone. And on those high pressure zone, the coarse particles stay on it. So in here, people, we have to talk about physics. And in this part, I have movement, and I have then this equation. I have the velocity, the mass, and that's the movement quantity. Okay, so if your particle have high movement quantity or high momentum, it's going to stay on the outer side of the hydrocyclone and it's going down. If the particle has low momentum, it's going to come to the center of the hydrocyclone and it's going up. And that's why you have so many different geometries in the hydrocyclone and hence applications. Okay, so first application, particle separation, okay, particle size separation. But second application, if I have two different materials, and by different I mean specific mass, for example, iron ore with specific mass like 5.03 grams per cubic centimeters, together with quartz 2.65, you can feed the hydrocyclone, design it to do this, and you can have the hematite going down and the quartz going up on the overflow, especially if all the particles has the same size. Okay, now I have particles with the same size and different masses, and I can separate. Okay, but on the third thing, I can remove water. So hydrocyclone can be used can use to dewatering, and that's what this simulation is showing you guys. Okay, but I can do also another thing. I can try to do hydrocyclone. It's not a concentration, but it's a pre-concentration. Okay, all of this hydrocyclone can do it. In some cases with better performance than in other cases. So depends on your material, depends what you have in hand. But the sliming is one of the best applications for hydrocyclone. What is this liming? Is the removal of the very fine particles present together with your ore, okay, or made by your ore. But hydrocyclone can do this. So the hydrocyclone is composed by the inlet, which is the part where I introduce my material in my hydrocyclone, the vortex finder, which is this tube in here, and the material is going to go around the tube after the feeding, and if it's go inside of the tube, game over for it. It's going to be collected and it's going to be transported to the overflow. So the vortex finder has to prevent the feeding material just to bypass the hydrocyclone and go straight to the overflow. Okay, and in the other side of the hydrocyclone we have the apex. The apex is this small area over here, is this constriction over here, as you can see also over here, that we going to make the cut, the particle size cut that I want for my hydrocyclone. Okay, the other operational variables is going to be all geometrically related to the hydrocyclone, would be like all the diameters, all the heights, and so on. Plus we have the pressure that I'm going to put my material, or the rate that I'm going to use to put material inside of the hydrocyclone, the flow, and also the solid percentage that I'm going to use in my equipment, because I can't control more than that. So I have also some videos in here for you guys to take a look. And these guys started very nicely. They have saying that the key challenge is water. Water is a problem. So let's try to use water better. And then Metsu, it's coming now with their own hydrocyclones. Because why is this so surprising? Because hydrocyclones is something so cheap that we used to make this. Was closed and you're good to go. So you can change your tire with your car moving and works pretty nicely. So Weir is the main manufacturer and they have this KVEX. And KVEX, it's according to them, okay, one of the top hydrocyclones in the world. And now they're putting the market, they're like KVEX version 2 or 2.0. And it's remarkable. They have this geometry completely different was expected, because we're expected to have like one cylindrical chamber followed by one conic chamber, and they can have different chambers on that, but they can have this spigot where you put the apex on different size and different places, and this actually do the trick. Okay, so you can see only with water is a good simulation just for you to understand how hydrocyclone starts, and then you can see the vortex being formed. Okay? So if you don't have this vortex inside of your hydrocyclone, you can have classification. Okay, so in our lab we start always with water, pure water. We expect for the vortex being formed, okay, and after that we start to add solids. Okay, and you can see over here that the guys They really know what they are doing, and they do a good job. Definitely do a good job on this. Okay, and that's the apex. And this bypass that I mentioned too is because it's quite easy to have your fine particles going together with the coarse particles. But if you change the geometry and if you change the operational conditions, you can't avoid this bypass, or you can at least minimize this bypass. And that's what they're showing you guys in here. Okay, so I think we can move on just for some hydrocyclone pictures from Brazil and Catalão. Okay, so you can see the hydrocyclones came in different colors, different shapes, but they do similar things. Okay, so those hydrocyclones are for classification, but I'm gonna show you guys those hydrocyclones for desliming. Okay, so if I move down on the particle size, I have to change the geometry of the hydrocyclone, and that's why we have those. And don't make any mistake, that's what we're going to see. If you take a look at the hydrocyclone, if you open this, you're gonna see something like this. And it's important for you to study this profile over here. Okay, according to the profile, you can see if your hydrocyclone is working as it should be, or if it's working poorly. Okay, and this one is the one in standby that I mentioned to you. Okay, it's not working. So this picture also taken here on the phosphate company. And next Tuesday, 7 p.m., we're gonna talk about milling. Okay, and again, I thank you all